Hello, Professor Ajayan. This is Avnish
Hey, how are you,
Srivastava.
Avnish?
I'm fine. How are you, Ajayan?
I'm fine. It's a bit
Uh,
early here, but
I can
otherwise I'm fine.
understand. Thanks a lot for accepting our invitation, Professor Chattopadhyay. I can see. I was traveling. I just came back today morning from Delhi to Bhopal.
Oh, okay. So traveling looks like it's happening in India at least.
It has started at least short distances, and we have to do that. There is no option. So
Yeah.
sometimes physical meetings, especially Delhi CSIR headquarters is there. So
Uh-huh. Yeah.
we have to do it. So yeah, in fact, in January month, I went 4 times to Delhi.
Oh, I see.
Yeah, and every time with full of scare, and then come back, and after 1 week, I find okay, I am fine. So that is how it is happening. So we are covering, in fact, around about 12 hours across the globe, starting from US to Italy to India.
You're right.
Yeah. It must be around 6:30 a.m. at your place.
Yeah, it's about 6:30.
Yeah, and 6 p.m. in Delhi, yes, Delhi, Bhopal, India, and around 1:30 p.m. in Italy. So we are covering. So this was the only time we could choose in the evening time where we can fix other speakers also. Otherwise, it was becoming difficult for us
Right,
when you
right.
have speakers from different countries. And this Professor Dasgupta's Memorial Workshop this is going to be like first time on his birthday.
Oh, really? Okay.
Yeah. And after completion of his 111th birthday anniversary. So we thought let us have this workshop and hope we will continue this culture now onwards in EMSI.
Wonderful.
And he was the person who built horizontal transmission electron microscope during year 1946 to 48 in India.
Hmm.
And I suppose that was the first TM built in Asia at that time in University of Calcutta. And later on, it is on display at Saha Institute of Nuclear Physics, Calcutta. And he was also the founder, president of Electron Microscope Society of India. So we should honor such great people. And our society is flourishing. Professor Chattopadhyay is doing very great mentoring of this society at present. And we have very stalwarts in this society, and that is why it is progressing well. We also organized this APM Asia Pacific Microscopy Conference last year in Hyderabad. It was about after 50 years. So things are happening in a good direction.
Sir,
I think within 2 minutes we will start the
sir, we can
proceedings.
start, sir.
Yeah, anytime. Yeah.
Chattopadhyay, sir.
Professor Chattopadhyay, can we start now? It's okay?
Yes, yes.
So, should I start, sir?
Yeah, sure.
So, a very warm greetings to all of you. Respected chairman of today's workshop, ACBRB Distinguished Fellow, Professor Kamanyo Chattopadhyay, President of Electron Microscope Society of India and Director CSIR-AMPRI, Professor Avnish Kumar Srivastava, distinguished speakers of today's workshop, Professor Pulikal M. Ajayan, Professor Andras E. Vladar, Professor Carlo S. Casari, respected dignitaries, EMSI community members, ladies and gentlemen, a very warm welcome to all of you for Professor N. Dasgupta's Memorial Workshop being jointly organized by EMSI and CSIR-AMPRI on Professor Gupta's 111th birth anniversary completion. On behalf of organizing committee, I welcome to all of you. Now, to start with, I request President EMSI, Professor Avnish Kumar Srivastava, for his welcome address. Sir, please. Sir. Thank you.
Welcome to Professor Dasgupta Memorial Workshop on his 111th birth anniversary completion, jointly being organized by Electron Microscope Society of India, in short EMSI, and CSIR Advanced Materials and Processes Research Institute, in short we call CSIR-AMPRI Bhopal. Professor Dasgupta was the founder president of Electron Microscope Society of India, which was established in the year 1961. His full name, Neeraj Nath Dasgupta. He obtained his PhD degree in 1938 from the University of London under supervision of Nobel laureate Sir C.V. Appleton and Professor C.D. Ellis, and a DSc degree from the University of Kalyani. At the inspiration of Professor Meghnad Saha, Professor Dasgupta started building electron microscope and developed Asia's first horizontal transmission electron microscope along with his students and colleagues at the Institute of Nuclear Physics, University of Calcutta during the year 1946 to 1948. His publications include 4 papers in Nature and 2 in Science. He served as head Biophysics Division, Saha Institute of Nuclear Physics during 1951 to 1969 as Sir Taraknath Palit Professor of Physics and Head Department of Physics, University of Calcutta, 1969 to 1974, and as Professor in Charge, Electron Microscope Center, University of Calcutta from 1974 to 1980. The Asia's first TM developed by Professor Dasgupta and his colleagues is at display in Saha Institute of Nuclear Physics, Calcutta. We are fortunate to have today with us Chairman of the workshop, Professor Kamanyo Chattopadhyay, a great Indian metallurgist, material scientist, and electron microscopist of international repute from Indian Institute of Science, Bangalore. We have 3 highly distinguished speakers today with us, Professor Pulikal M. Ajayan from University of Rice, Houston, Texas, USA, Professor Andras E. Valadar from National Institute of Standards and Technology, NIST, Gaithersburg, USA, and Professor Carlo S. Casari from Politecnico di Milano, Department of Energy, Italy. In addition to that, although we are on a virtual platform, of the dais, we have very distinguished senior people and scientists, faculties, audience who are participating in this presentation. Some of them directly connected to our this Zoom, some of them are YouTube. So in the beginning, it's difficult to make out, but we have very senior people who have joined this gathering. I welcome all of them on behalf of Electron Microscope Society of India, CSIR Advanced Materials Process Research Institute, Bhopal, and also on my personal behalf to this very, very important workshop in the memory of Professor Anand Dasgupta on his 111th birthday anniversary. With this brief note, thank you very much and all the best wishes for this event. Thank you very much. Namaskar.
Thank you, sir. Now, it is a privilege for us to have Professor Kamanyo Chattopadhyay as today's workshop chairman. Professor Kamanyo Chattopadhyay is a SCRB Distinguished Fellow and Honorary Professor at Indian Institute of Science, Bangalore. He is Chair of the Mechanical Science Division of IASC and former Chair of Department of Materials Engineering. He is a very well-known material scientist all across the globe and known for his extensive work in decagonal nanoquantum quasicrystal synthesis and characterization. Professor Chattopadhyay has more than 350 publications. He is also elected fellow of all the 3 major Indian science academics and has received number of awards. He is also recipient of one of the highest Indian Science Awards, Shanti Swarup Bhatnagar Award for Science and Technology for his contribution in engineering sciences. Now I invite Professor Kamani Chattopadhyay for his address. Sir, please. Thank you.
Well, I think we have to develop the culture of online meetings. We are still following the format of regular meetings, but thank you very much for introducing me, Archana, and I'll be very brief. I don't have much to speak because we rather want to listen to all the three distinguished speakers here. Only briefly, I must say that the occasion is very important because it's the 111th birthday of N.N. Dasgupta, and electron microscopy, what we see it in India, has been started by him much before the advent of commercial microscope. In fact, his students, Professor Bhattacharya, actually bought the first Siemens electron microscope in India when he was a faculty at Indian Institute of Science in 1950. And then he went on to get first microscope at BHU in the Department of Physics, and later, of course, he returned to Calcutta. So the influence of N.N. Dasgupta is very long, and Ajayan will have not seen Professor Bhattacharya, but I, as a faculty of BHU, seen him. As a student, I have seen him. Now, from that point onward, we have made progress. We have now part of International Federation for Society of Microscopy, and our society is daily gaining steam. And what is more important, we have a support of all these distinguished microscopists all over the world. That is proven by the presence of three distinguished microscopists and scientists in this gathering. So without wasting much time, I would rather like to listen to all of them. So, Archana.
Thank you so much, sir. It's always pleasure to hear us, sir. You, sir. Thank you. Now to go ahead, I request before we start the presentation, I request Dr. Naren, CSIR-AMPRI scientist, to screen short video on tribute to Professor Neeraj Dasgupta.
Hello, Dr. Satish, there is no audio, so please reshare that. I'll share, sir.
Professor N.N. Dasgupta, a trailblazer in electron microscopy in Asia, made commendable research and also contributed substantially to other fields of biophysics. Neeraj was born on February 1, 1909 at Chittagong, now in Bangladesh. He was the eldest son of the late Ganga Charan and Indulekha Dasgupta. Neeraj Nath received his early education from Hindu school and graduated from the Presidency College in the year 1929. He studied physics in his postgraduate course and obtained his master's degree from the University of
Unmuted.
in 1931. He stood first in the MSc examination and was awarded the University Gold Medal. After obtaining the master's degree, Neeraj Nath approached Professor C.V. Raman, the head of the Department of Physics, to undertake research under his guidance. Professor Raman readily agreed to take him on as a research scholar. In 1932, Neeraj Nath obtained a state scholarship to work in the University of London, UK, and subsequently moved there to pursue research work, leading to a PhD. He was fortunate to have as his research guide Professor C.D. Ellis, FRS, the Wheatstone Professor of Physics in London University and a colleague of Lord Rutherford. After obtaining his PhD on nuclear physics, Dr. N.N. Dasgupta returned to Calcutta in June 1938 and met Professor M.N. Shah. He joined as a lecturer in physics at the Calcutta University and began investigations in the emerging area of cosmic rays and soon published a paper in the prestigious journal Reviews in Modern Physics. This paper was highly acclaimed and referred to in many textbooks in the field. From his personal diary, we came to know that Professor Dasgupta strongly felt that modern instruments would help research which would ultimately help in the development of our country. Such instruments were essential for the emerging field of material as well as in biological sciences. Professor M.N. Shah encouraged Professor Dasgupta to move to Stanford University on a sabbatical to work with Professor L. Martin, who had, at that time, successfully completed fabrication of an electron microscope there. On returning to Calcutta, Professor Dasgupta started fabricating the horizontal electron microscope indigenously at the Calcutta University with Sri M. L. Dey, Sri D. L. Bhattacharya and Sri A. K. Chaudhary as his trusted lieutenants. An Oriental scholar and philanthropist, Dr. P.C. Law, donated an amount of Rs 17,500 on account of this. Looking at the complexities of the components of the electron microscope, we can at once appreciate the dedication of this team and the Herculean task they had to perform in accomplishing their mission. It is indeed a matter of wonder when we look back at their achievements from the present era of automation. 1948 was the glorious year in Indian science, when the first horizontal transmission electron microscope was successfully commissioned and it started its operation. This came into operation even before the first electron microscope manufactured by the Japanese, the world leaders in this field. It is Professor Dasgupta's initiative that led to the inauguration of the Electron Microscope Society at Calcutta on December 2, 1961. He was the founder president of the society, with his headquarters at Shah Institute of Nuclear Physics. University of Kolkata acknowledged his contribution to science by awarding him an honorary doctoral degree. Professor Dasgupta was also elected the Fellow of the National Academy of Science in 1958. After a brief illness, he passed away on August 15, 1999, at his Hajra Road residence in Kolkata. He was religious in mind and loved devotional songs. He had a genuine love for his students. He led a simple life and would believe that scientific achievements are not for name and fame. He worked for the betterment of science that would benefit his country. As a tribute to this great researcher and teacher, it is our endeavor to disseminate information about his life and work in order to keep his mission alive in the hearts of young researchers.
Thank you, Dr. Naren. It's really inspiring story of Professor Dasgupta and encouraging for young scientists. Now to go ahead, we are really honored to have Professor Pulikal M. Ajian for the opening lecture for today's workshop. He has a very impressive long list of achievements, which is really difficult to put in few words. Professor Ajian is a Benjamin M. and Mary Greenwood Anderson Professor in Engineering at Rice University, USA. He has expertise in synthesis and structure property relations of nanostructures, nanocomposite material science, and application of these materials in number of applications. He has published more than 1,000 research articles with impressive 95,000 citations, and he having an H index of 150. He has also received number of awards like SPAS Memorial Award by Royal Society of Chemistry, Senior Humboldt Prize, MRS Medal, and so on. There is very long list. He is one of the pioneers in the field of carbon nanotubes. Also has been part of 2 Guinness Book of World Records, one for the creation of smallest brush and the other for creating the darkest material. I invite Professor Ajian for his opening lecture in today's Professor N.N. Das Gupta Memorial Workshop on Material Science in 2 Dimensions. Professor Ajian, please.
Thank you. You can hear me well, I suppose, right?
Yes, yes, sir. You are audible, sir.
Okay, so let me share my screen.
Yeah.
Can you see it?
Yes, sir. It's visible, sir. Yeah.
Okay. So good afternoon, everyone. Good morning from here. First of all, let me thank the organizers for inviting me. It's really an honor to be I heard that it's the first endowed lecture for Professor N.N. Dasgupta. It's always wonderful to be in a place, well, these days it's all online, but still with folks that you have known for many, many years. And, I can see many of our friends and that I know very well in the audience. So thank you again for this opportunity. I have known of Professor Dasgupta for quite a while. It was very informative to see that video on what he exactly did. Science is really a cumulative process, and we build on what others have done before. And particularly someone with some background in electron microscopy, I can appreciate the challenges that Professor Dasgupta would have had when he was building. And it's amazing how the microscopes have changed, over the years. Even what the microscope that I trained on maybe 20 years ago, is nothing in comparison to what we have today. So it's really amazing how things move and how fast things move. Well, I mean, today, I was going to kind of share a few things that we have done over the years in this new area of extremely thin materials, or people call it 2-dimensional atomic layered materials. And there will be quite a bit of microscopy that I'll be showing. And I also want to say that some of these things were done by students who have actually gone back to India and has become faculty in different institutes in India. Chandrasekhar, for example, is a faculty in IIT Kharagpur. Vidya is also there. I mean, many of these work that I'm going to show has connections to what people have done, and you know, especially for faculty in India now. You know, as it was mentioned, you know, I started my career with carbon nanotubes and moved on with many other materials. We do a lot of different things in our lab, including some energy storage and 3D printing and so on. And today's talk is just a slice of this particular area that we have developed over the years. And this started with the discovery of graphene, as we all know, and it has kind of blossomed into a lot of different types of compositions and structures. So it's really a very large field now, and what you will see is just a few things that we have focused in our lab. And this fascination with layered structures go back a long time. Even from Feynman's time, people were kind of interested in these type of materials because it's got a very anisotropic kind of bonding. You have these strong in-plane bonds, and there are these van der Waals forces that connect layers. And there's always this fascination that, you know, how can I peel off these layers and then do something with it? Or if I stack these layers with different compositions, what kind of properties would emerge? So I think it's kind of a very unique set of materials that exist in nature, and people have been able to make it synthetically. So this whole field has become an exploration into this uniqueness in these type of van der Waals architectures and what one could do with these. And there's some really exciting stuff that is happening these days about, you know, taking these layers and twisting them a little bit and trying to see how rotational disorder can create some you know, strongly correlated systems and so on. So the list goes on. And what I'm going to say is mostly from the materials aspect of things, but there's a huge body of work that is going on that looks at the physics of this and also how properties emerge when you do some kind of engineering with these layers. And this is just an illustration to see what these structures look like. So what you're seeing is a layer of molybdenum sulfide that is wrapping around a step in silicon. And you can see it's really, you know, one could do these days very large area synthesis of type of layered material. And even this image kind of tells you what kind of challenges that you face. As you move these things around, you know, you start seeing all these simple defects like blisters and, you know, ripples and things like that. This is, you know, it's interesting to see this, but end of the day, they would have significant impact on the ultimate properties that you want to get. So on the one hand, you know, progress has been made. On the other hand, we still struggle with some of these intrinsic issues that could change the properties fundamentally. Just to emphasize this point, here is some work that we did in collaboration a long time ago, showing that you know, if you wrap around some features that exist on the substrate and then look at the electronic properties, you see significant differences where the strain is concentrated. For example, you know, where the tips of these features, where the molybdenum sulfide is wrapped around, you tend to get more metallic nature of these molybdenum sulfide compared to the typical semiconductors. You know, if you combine this with the previous slide, you can imagine the kind of difficulty that you might have when you are really trying to build devices and so on. So small perturbations can introduce some significant changes in behavior. I mean, in some sense, this is actually a broader issue with nanomaterials because the structure property correlations are very strong. At the same time, manufacturing doesn't allow you to make structures that are very precise and that can be controlled at the atomic scale. But again, with 2D materials, one could see that this is exhibited in a significant here is actually another example why such thin materials are kind of unique. Quite a while ago, we were one of the early ones to suggest that there could be a transparency of properties if you put 2D material as barrier layers. In fact, we showed that if you put a couple of layers of graphene on a substrate, the wetting behavior of the substrate can remain unchanged because there is some level of transparency, not just optically, but also in other properties. Here is another example of the same idea, that if I kind of cover materials with these extremely thin layers of graphene or boron nitride or layers like that, you could still preserve the underlying property of the substrate or the material that is underlying. In this particular case, we covered this cobalt oxide, which is a catalyst for oxygen evolution reaction. And the properties of the CO304 remained unchanged when you had a complete coverage of these structures with a single layer of graphene. So the point is that because of the thinness, charge transfer and behavior like that could exist even through a completely uniform overlayer, which could have really spectacular outcomes. For example, you could protect things from oxidation, still preserve substrate properties or surface properties, and so on and so forth. And even recently, a group from MIT showed that you could even get epitaxial growth with a barrier layer or an intermediate layer of graphene sitting on the substrate, which is quite amazing, because if you can do that, then you can create super thin layers of another material on a substrate and just simply peel it off because you have these graphene layer in between. So I think super thinness or extreme thinness brings some uniqueness to these materials. And of course, then there is all kinds of device potential for these materials. Here is some work done with our group, Santa Barbara group, suggesting that you could build these two-dimensional channel tunnel FETs, which not only takes care of some of the electrostatics that is a problem with silicon as you scale it down, but also with some fundamental thermodynamic constraints like the turn-on voltage. Typically in electronics, when you go to very small scales, things don't scale like the gate voltage or the turn-on voltage doesn't really scale with the scaling down of the device structures. But it is shown that if you can find the right kind of architecture and right kind of devices, like a band-to-band tunneling device in this case, then you can avoid some of these problems and even break the thermodynamic barriers. So there is that part of the 2D material systems where people are looking at new architectures for devices and so on. So with that kind of a preface, I want to kind of talk about a few things that is more related to materials. I'll mention about some of these building blocks and how you can create them, and then go into more interesting things like stacked structures and planar and lateral interfaces. Then talk a little bit about phase stability, which again is very curious, especially if you go to multi-component systems, how diffusion occurs in 2 dimensions and so on. And also a little bit about, depending on the time, other kinds of structures that includes these type of 2D materials. Now there is a significant range of compositions that one can build and that exist in this format, all the way from graphene, which is a single element, basic carbon-based material, to hexagonal boron nitride, to transition metal dichalcogenides, and so on. And again, it spans the entire spectrum of electronic properties, all the way from metallic to insulating. So within these systems, we can pick and choose whatever you want in terms of electronic properties or chemical behavior, because there are quite a few of these family of layer systems. even if you don't have layered, per se, there could also be potential or approaches that allows you to break down or cleave along certain crystallographic planes and create extremely thin layers, which could be very similar to the layered system that we're talking about. Again, this is just an example to show one of the typical procedures we use to create these two-dimensional materials. That is essentially chemical exfoliation. Of course, in a layered system, it's much easier to see that things would cleave along the basal planes. But even systems that are not traditionally layered, like in this particular case, you're seeing an example of iron oxide, one could cleave along certain directions if the conditions are right. And then you can explore the properties of these super thin layers of these. And the hematite or alpha iron oxide, which is not truly magnetic, appears to have some magnetic properties when you go to very, very thin levels. The other procedures that people have followed is the physical exfoliation. And again, as we all know, the Nobel Prize was given to people who were able to exfoliate graphene layers by a Scotch tape. Exploration of those layers. And there are many different ways of physically exfoliating materials. Scotch tape is one of them. You could also just have a stamping technique where you can pick up very thin layers from solids or even liquids. And what you're seeing here in this case is actually a solid melt exfoliation technique where a gallium, which becomes molten at reasonable temperatures, one could go with the substrate and pick up super thin layers and then explore those gallium layers. We actually called it gallium. And you can see that, again, this retains the metallic nature of gallium. In fact, there are not too many systems that are truly metallic when it comes to 2D systems. So this was an interesting structure which possibly could have applications as compacts and so on and so forth. The final technique that we normally use in our lab is vapor phase deposition, and this has been the most common technique to grow large area scalable type of structures. And I'll show you a couple of instances. This one particularly was a recent study where we were able to deposit super thin layers of tellurium. And tellurium is an interesting material, and even materials like sulfur, selenium, they all follow this pattern. It forms in various types of structures, and it has different unit cells depending on what kind of phase you form these in. We were able to create really almost atomically thin layers of tellurium and explore the properties. Of course, I don't have too much time to go into this. Just wanted to show the different possibilities in terms of material synthesis. And again, this is actually a very nice review article that we collaborated to write with Nick from Air Force Labs. And this shows the different elemental materials that people have been able to create over the years, all the way from graphene to, you can see, all kinds of elements that have various electronics, optoelectronics, and even electrochemical properties. So this has been kind of an evolving field, as I said. And whether it is a single component system or two component or multi-component, there's been lots and lots of studies that tell you how to synthesize this in reasonable size. And you can see the entire spectrum of crystal structures in these. And as you go thinner and thinner, you also might see some modifications to the structure. And we'll talk about that in a little bit more detail later on. But just shows you the variety of structures that you create from even simple single component systems. And most of the work, of course, has been focused on two components, and particularly in this area of transition metal dichalcozanide. And by CVD, you can grow all kinds of sulfides. In fact, this review in Nature kind of talks about a broad range of material systems and grow by CVD using various tricks to get uniform layers of all these different And we were, again, one of the early ones to start to grow these by CVD. We used metal oxide precursor, and we were able to sulfurize or selenize these to get thin monolayer, meaning molysulfide as kind of a stack in a single unit of thickness. We were able to grow very large area structures as early as 13, and a lot of people have followed this approach to make large area systems of these materials. Now, one thing to notice is that defects, of course, become very important, and it's quite hard to control defects. And we were also interested in looking at what kind of defects exist in these materials, what kind of grain boundaries form in these structures, and so on. So, graphene is a very interesting example because a lot is known about defects in carbon, particularly these topological defects like. And people have again looked at these in more detail and found these topological defects at grain boundaries. And there's also suggestions that depending on how these grain boundary structures are created, you could in fact have a significant scattering of electrons or even tunneling of electrons. Some of these things have not been experimentally verified, but certainly it looks fascinating that such grain boundaries would exist and with the properties that they're. Very similar thing with other structures like molybdenum sulfide. Of course, the grain boundary is a little bit more complicated than graphene because you could have, it's a two-component system, and you can have defects that relate to sulfur vacancies or metal vacancies. And but in general, there's been predictions and experimental proof that these type of topological defects do exist in the grain boundaries of transition metal dichalcogenides as well. One of the interesting things that we have pursued in our lab is to see how large crystals you can grow. And as you can see, you could indeed, by optimizing conditions, grow millimeter-sized grains, millimeter-sized crystals of these without any grain boundaries. Doesn't exclude other kinds of defects like point defects, but certainly you can grow single crystals of these over large area. And again, most of these has been trial and error and finding the right conditions. Again, as I said, there are other various intrinsic point defects in these materials. I don't have time to go into these, but certainly this paper is a good reference to looking at different types of it's kind of curious that materials like molybdenum sulfide has been looked at by many, many people over the years for catalysis, lubrication. But very detailed atomic studies are missing from these materials. And it's only after these single monolayers were available that one could make very nice single crystals or maybe thin layers and then study them by electron microscopy. So, even in the last few years, significant contributions have been made into the actual structure of some of these dichalcogenides, although it existed for a very long time. And again, it's very clear that depending on the way you grow them or the process that you use, the density of defects can be quite different. This is not our work, but it is from Jim Horn's work in Columbia. We were actually part of a joint while. Shows that one could tweak the growth technique to decrease the defect density significantly. And this is very important, finally, if you want to use them for semiconductor device applications. The other option is, if you think about defects, you can intentionally create defects in these. There are a couple of ways that we have done. One is by hydrogen exposure or by oxygen plasma exposure. And these different types of chemical, vapor phase chemical reactions lead to different types of various types of holes in this material, or you can actually create fractures. We've done quite a bit of work in trying to expose these to various gases and then finding out what is happening. And these can also be very useful if you're creating intentional structures by vapor phase reactions. You can also use them later for improved catalysis and so on. Again, these are all different types of material science you can do with these 2D layers and leading to some specific applications. The other possibility is to actually nanostructure these 2D layers. So you could create ribbons of these, you can dope them, and then again, one could see that there's significant impact of these defects, including edge sites, including grain boundaries, point defects to the ultimate performance of these materials in different applications. Just a couple of slides on different types of 2D two-component systems. We mostly talk about sulfides and selenites, but there are also oxides which are interesting. Molybdenum dioxide, which is not really the most thermodynamically stable oxide, has some very interesting properties. And particularly, we recently pursued the idea of electrodes. And this happens because because of the intrinsic stoichiometry defects. You can create polarized charges, and because although moly oxide is not really a piezoelectric material, because of this intrinsic defects that appear from non-stoichiometry, you can create piezoelectricity in these layers. This is actually, I think, published recently in ACS Nano. You could actually go and look at it. So let me move on quickly to the more interesting part of this 2D systems, and that is really stacking these. So obviously, many of these systems are intrinsically stacked from strong in-plane bonded layers. Boron nitride, they're all stacking of multiple layers. But when you stack, you can think about these rotational disorder that I mentioned. And that allows you to have various isomers for these structures with significantly different properties. So the idea would be to think about building these heterostructures from 2D layers with different compositions. The question really is how much control you can have and what kind of emerging properties you can find when you do this type of material science. And again, the major challenge here is how do you really build with control certain types of stacking? And depending on the kind of stacking you can get different types of balance and so on. Now, to complicate matter, many of these transition metal dichalcogenides exist in multiple phases. Some of them are metallic, some of them are semiconducting. So people talk about these 2H phases, which are semiconducting. Again, it depends on how the orientation between the different layers are, or between the metal and the chalcogen atoms in each of these layers. And sometimes you can also find this 1T prime phase, which is more metallic. So again, when you're trying to stack using some kind of growth technique, one also finds this challenge of what phase forms and under what conditions, and can you actually control them? I'll give you a few examples of these as we go along. And again, ultimately, if you want to build up these stacks, it would be quite challenging on how exactly you do this by vapor phase deposition. Each layer is only a few angstroms thick. So if you want to get a reasonably thick film, you have to do these multiple times, or in single growth step, you need to bring in multiple precursors and grow for long periods of time. So the growth itself is kind of challenging. And as I said, it's mostly optimization approach. Now, there is also another issue. If you are particularly interested in stacking different compositional layers, because then either it can form one on top of the other, or you can actually form lateral structures, because many of these structures that we are trying to combine in stacking is isostructural. So if you take something like boron nitride or graphene, their lattice parameters are very similar. As they grow, they can not only stack one on top of the other, but they can also get stitched together in a lateral junction. The same story with many of the dichalcogenides. So end of the day, when you're trying to grow them, you end up with all these mismatch of various structures, both in plane and out of plane. And in outer plane, as I said, one could have different types of stacking. the preferred 2H stacking, which leads to more semiconducting type of material, or we call it the 3R stacking. So there again, stacking could be quite complex when it comes to these materials. So again, a lot of microscopy that we have done over the years to show that under conditions you can actually get these preferred 2H stacking, or under lower temperature, one could get systems that grow in plane heterostructures. You can see this very beautiful, almost atomically sharp junctions that exist between different compositions of this is actually a larger view. And then one wonders how sharp, I mean, although these are atomically sharp, how stable these interfaces are. We're able to create a very nice junction between, let's say, tungsten sulfide and molybdenum sulfide. How does this junction remain stable? Can you have fusion across this interface and what conditions? So these are some of the questions that we have asked, and obviously you can find some diffusional layer around this interface that changes as you change parameters like temperature. And finally, very recently, people have been trying to think about this idea of twistronics. So if you take 2 layers and then start to twist or start to rotationally disorder, then you start getting these mores, and they apparently have very strong effect creating some very fascinating maybe one could think about interlayer excitons when you are twisting them. There's some correlated systems which even show some superconductivity in bilayer twisted graphene. So this is again become another field in itself, trying to see how one could controllably create these type of twisted structures. And there are many techniques to actually explore the electronic properties. In one of these recent studies, we have followed low electron energy loss spectroscopy, but people also can do transport and other things to understand how the correlation occurs between these twisted states and the electronic structure. Again, there are lots of possibilities. I'm just showing you a few. The other option is, because these transition metal dichalcogenides are almost a 3-layer system with the metal sitting in the middle and the chalcogens on either side, one could think about replacing the chalcogen atoms with another one on one side. So you could end up with this Janus kind of architecture. And they also have a different behavior. But again, it gives you a curious way to think about modifying some of these structures by growth or replacement, substitutional doping, and so on. So, again, as you can see, there are various ways you can modify these structures, either through stacking or through replacement of specific ions. And you can end up with some really interesting broad range of Now let me talk a little bit about this phase stability that I mentioned in the beginning. Especially as you go to multi-component systems, you can see that the phases that form could be either segregated or mixed. I'll first talk about these segregated systems where you can form domains that are entirely separated but stay within the monolayer. And in particular, this phase diagram of boron, carbon, and nitrogen has lots of phases that follow this pattern. We were specifically interested in looking at mixing the boron, nitrogen, and carbon and seeing how the phases remain as you change temperatures of growth and so on. And in general, what we find is that boron and nitrogen has a strong tendency to go together, and carbon with carbon separate. So if you make a growth with these different precursors to make a graphitized B and C system, you end up with what you're seeing on the right image, kind of a patchwork of domains. And depending on the conditions of growth, you can get nanocrystalline or microcrystalline domains of the completely segregated boron nitride and graphene. And it's interesting because boron nitride is a very large band gap material. It's almost a 6 eV band gap, very non-conducting. And graphene is a metallic structure. So if you create a domain structure like this, it's very interesting to see what kind of properties would emerge. And there are various ways of doing it. Either you can grow directly these layers with the precursors that I mentioned to you, or you could start with carbon and actually convert that carbon into boron nitride using high temperature reactions. And we can follow these pretty nicely, how some of these PMC systems are formed. But I just wanted to mention that because there are various different ways of growing these structures. Again, just like graphene or graphitic structures, these kind of films can be grown highly crystallized with all these three components. But if you look more carefully, you will see this domain structure that I mentioned. And we have been, again, in the recent years, trying to figure out how to control these domain formation, either by growing one layer of one composition, etching it out, and then regrowing in those gaps, and things like that. We were able to create all these beautiful patterns with periodic arrangement of one of those domains. So, for example, you can take graphene and etch parts of it and regrow boron nitride in those gaps. So you get these two-dimensional heterostructure all in plane. And one can think of structures like this as, for example, an antenna, all 2D antenna structures. It's metallic and insulating matrix. So there's all kinds of engineering that you can do at the nanoscale within these two-dimensional layers. And that's been really very, very interesting. And some patterns that you're seeing where we have managed to create different types of in-plane architectures of boron nitride and graphene. There is another system that we have also been playing around with, very similar to the boron nitride and graphene for the in-plane heterostructure. But this is different because these are compositionally the same. So you could still create a two-dimensional heterostructure with the same composition of molybdenite, but different phases. So as I said before, many of these transition metal dichalcogenides have different phases. So 2H and 1T prime, one of them is semiconducting, the other one is metallic. And if you try to grow molybdenite just under a range of conditions, typically you end up with a mixture of these two phases. Thermodynamically, they're kind of similar in energy. And if you see that image, you can see there's a 2H and the 1T prime, which is slightly different in structure, although the lattice parameters are rather close. So you could get these rather strained but in-plane stitched together heterostructure. And one thing we were trying to do was to make this 2H structure as a channel for a device, and the 1T prime, which is more metallic, as a contact layer. And we were able to do that. You grow these structures, go around and search for these different phases, and then put your contact on the 1T prime area, and you get pretty good devices if you do that. But of course, it would be much nicer if you can controllably create these in the locations that you want. For example, can you create a molybdenum telluride structure and then go around using some kind of stimulus to change it to a 1T prime? Then you know exactly where you put the contacts rather than going and searching for them. And as you can see, there are so many high impact papers based on this idea of locally changing or phase patterning, essentially. But that's, again, a tedious process if you want to kind of go and post-process. So one thing we were actually interested in is to see if you can controllably create these heterostructures in a periodic fashion during growth process. And one thing we realized is that if I take telluride and start to dope them with another metal, like, if I take molybdenum telluride and start to make doping with tungsten, then it goes towards the more metallic phase. So tungsten telluride is actually metallic. It doesn't really easily form a semiconducting phase. And doped molybdenum telluride with tungsten actually gets more metallic nature. So we thought that it would be an interesting way to create these periodic structures by creating a sub-layer of tungsten first and then growing the molybdenum telluride, so that the tungsten would diffuse and then create these metallic 1T. So by this technique, we were actually able to make large area of repeating patterns of 1T prime and 2H by simply having these underlying tungsten regions that create this diffuse layer of molybdenum telluride, which forms the 1T prime. So one could do all kinds of tricks like this to actually get these periodic structures and in-plane junctions that you want, which is very, very interesting. Not only that, recently, very recently, it's actually unpublished work, we were seeing that if you're looking at the piezoelectric behavior of these lateral structure, then of course the 2H is slightly piezoelectric and the 1T not. But we were seeing that at the junctions, you have an amplification of this piezoelectric. And the reason for this is some kind of charge transfer that is happening between the semiconducting and metallic interface at the junction. And again, remember, these are all essentially in the lateral direction, because you are essentially looking at a single unit thickness of these type of structures. And the final thing is, again, going from two components to increasing the number of components, going to ternary systems or tertiary systems, and seeing how they mix kind of chalcogenide systems. Again, as I said, lots of work has been done on these kind of materials like molybdenum sulfide in catalysis and many practical applications. But atomically speaking, very little is understood. For example, when you dope them. In fact, doping is actually a technique to increase catalytic activity, and this has been practiced by people who are working in these areas, but never really correlated with how exactly the structure changes as you do doping. So again, we did a lot of work in the last many years on understanding how exactly you can dope them and how they distribute in these two-dimensional layers. And unlike the segregated systems that you saw in the dichalcogenide systems, if you add elements which are at least compatible, like selenium in sulfides or different type of transition metals in these systems, they tend to distribute nicely and form alloys. And you can control the band gap within a certain range by changing the concentration dopants. And again, these are some of the examples that we have worked on: moly selenium telluride, tungsten selenium telluride. And again, these are all really nice microscopy work based on some of these distributed alloys. In fact, before we actually got a good microscope price, it's a Titan, we were working with Oak Ridge National Lab, and a lot of the images that you're seeing here is actually from Oak Ridge, the energy filtered imaging. So if you have multi-component system, 3-component or more, and end of the day, you can get either a totally random distribution or partly random or even completely segregated heterostructure. If you look at the selenium and the tellurium sites, and again, this has been seen. But again, before going in and showing some of these potential phase engineering by temperature and other parameters, let me also mention that as you go from binary to quaternary systems, the point that you can do is to change your band gap in a much more significant way. And again, these are some theoretical analysis that shows that as you go from binary to quaternary, you can expand the range of band gaps by changing the electronic structure. So it's always interesting to go to the higher component system. And here is actually a beautiful image from the molybdenum, tungsten, sulfur, selenium alloy, a single layer or single unit thickness of these. And you could see map very nicely the various arrangements of sulfur and selenium in these kind of alloy layers. And again, one of the goals is to kind of look at these type of structures for catalysis, electronic properties, transport. And some of these are ongoing, but again, one has to optimize and make sure that what you're getting is consistent from things that you see in electron microscopy, even at a larger scale. So the phase stability, as I said, you could heat them. You can create these multi-component systems like this is a moly tungsten sulfur selenium alloy that you saw. And by heating, you can actually make them to segregate. Again, the idea of phase stability within 2 dimensions is really not well studied. These are opportunities for us to actually do in situ studies and so on how these lateral interfaces become unstable and how diffusion across these interfaces happen. So there's a lot of beautiful in situ electron microscopy studies that you can do with these type of systems because they undergo this type of phase segregation. Or you could look at the effect of alloying, for example, you add something like tin, which is a non-isomorphous with these systems, you can, addition of those type of elements can also create the segregation, just like what you saw. So once again, broadly speaking, very little is done so far in these multi-component system of these chalcogenides. And there's a lot of potential in trying to understand the structure as well as the structure property correlations in these type of materials. Probably I have about 10 more minutes, so I quickly will go through some of the other things that we have done, not just growth part. We've also been looking at a lot of chemistry, chemical modifications, and creating low-dimensional structures from these 2-dimensional systems. Obviously, the most studied is the graphene oxide. People have looked at this for many years now, understood what kind of functional groups attached to the graphene basal plane as you oxidize them. And by various techniques, including the Hammers method, the modified Hammers method, there's a huge amount of literature that exists in the space. But still, one thing to say is that still what you end up with is a random distribution of functionalities. I don't think there's been any chemistry that is designed just to get a certain type of functionalities. It would be very interesting to see if one can design a chemistry that allows you to make purely graphene epoxide or something like that. But nevertheless, I think some of these are done to change the broad range of properties like reactivity or band structure and so on. And people have successfully done this. Graphene oxide is also very well used in energy storage nowadays. A more difficult material to kind of chemically modify is boron nitride, which is a very unreactive system. But recently, we have been able to do this. There's a bunch of other groups that have also accomplished boron nitride. But fluorination in particular has been interesting for us. Again, this is a technique that we published some years ago on kind of a chemical way of fluorinating this. Recently, we have started to do some vapor phase fluorination, and addition of fluorine to boron nitride creates some really interesting structure. Again, there's hardly anything in literature, but they also show some properties like magnetism, at least slight amount of magnetism in this kind of material. So modification of chemically modifying these structures is certainly possible, and that allows you another degree of freedom to work in the space. But most of the time, chemical modification creates a different topology. They kind of the sp2 hybridization is broken, and you get more sp3 type of structures when you are actually covalently modifying them. But there are also other ways of modifying very, very weak chemical processes. Again, this is a paper that we published a few years ago. It's based on Lewis acid-base chemistry, where you can create complexes without actually disturbing the topology of the underlying layer to create local regions of different electron density. And this might be interesting if you really don't want to break up the structure, but simply change the surface electron density. Or intercalation. And again, I don't have too much time to go into intercalation, but intercalation has been very popular in layered systems because it's easy to kind of push the layers apart and put other host atoms into these layered systems. And recently we have also done some non-traditional intercalation approaches. In fact, mixing copper and some of these TMDs and heating them to a certain temperature allows you to nicely intercalate the metallic atoms within the host galleries. So again, these change behavior significantly. As you probably know, intercalation has been done during the 60s and 70s in graphite. And there is a humongous volume of work in the graphite intercalation compounds. And there are still lots of opportunities for creating intercalated structures from other layer systems. Or you could also attach functionalities to the surface. Example of self-assembled monolayers being added to the surface of some of these layers, which change the electronic structure. So you can also modify it by simply adding acceptance layers or donor layers onto the surface, and then if you do harsh chemical treatments, these kind of structures break down very easily. And we've also been looking at how nicely you can break up these two-dimensional layers into quantum dots and quantum disks, maybe, because they are two-dimensional in nature. And graphene was obviously, there's a lot of work that graphene. And you can these days get quite a range of optical behavior pretty much through the entire spectrum of light. You can get the colors by either doping or by changing the size of these quantum disks. So that's again a totally different field in itself, and a lot of people are working on this. Some of these quantum dots are also catalytically very active because it's got large number of edge atoms, and again, if you dope it, that's even more interesting. So one of the things that we have done is this carbon-nitrogen quantum dots, which seem to be quite effective in CO2 reduction, which is again a hot field, but depends on what kind of dopants you can get into the carbon lattice and how large these quantum dots are. You get different performance. One recent work that we showed where we could get very facile breakup of these layers is by simply doing a pre-treatment of liquid nitrogen. So if you dump some of these layers into liquid nitrogen, they kind of stiffen up. And then when you do a sonication-based breakup, you get much more uniform quantum dots. So this is just another trick that one could use to get more higher yield of quantum dots and more uniform quantum dots because of this type of, I mean, maybe you could also do cryomilling, which would give you a similar kind of result, but this was a simpler way of doing this. So I think given that I have only a few minutes, I want to skip this, this section. So essentially, the idea I was going to talk about was how 2D layers could be embedded in other matrices or even built into three-dimensional architectures like foams and stuff like that, interconnected graphene layers, for example, and how the mechanothermal behavior could be engineered from these type of two-dimensional layers. So let me skip that part. It was just a few slides, but let me come to the conclusion. What we have been doing is to kind of optimize lots of things, play around with these layers. Of course, this is trying to be creative, but I think we are all, people working in this field want to see more controlled approaches, especially if you want to make these into devices and so on, controlled growth processes, large scale synthesis, roll-to-roll manufacturing, finding the sweet spot where you can identify the right kind of defects in these systems. Or is there a way to, rather than just picking and placing, is there a way to controllably create these twisted layers? So there are lots of exciting questions, but just like any other area in nanotechnology, I think control is the key factor that has been missing. And oftentimes it's kind of difficult because many of the nano manufacturing techniques bring in this intrinsic variability into the material systems. And I think we are, this is where we are, but nevertheless, we have been able to make significant progress in creating these structures, studying these structures, understanding them. Some of these things like diffusion of atoms in two-dimensional layers. It's a fascinating study, both for microscopy and many other techniques. So I think I will kind of stop there by simply acknowledging some of the funding that we have received and many people involved. We have a lot of collaborators all over the world, and that is what makes it much more interesting. So thank you very much, and hopefully some of us will see each other soon, after all these travel bans and stuff like that. Hopefully this year will be much better, and I really look forward to coming and visiting some of you in India. Thank you.
Thank you so much, Professor Arjun, for this very informative talk on uniqueness of 2D material, chalcogenides, multi-component chalcogenides, their interesting property and challenges. And we would really like to come here. We would like to come here, and it will be interesting to hear. I hope that COVID goes away and you visit us sometime in soon.
Thank you.
So yeah, now we can have 2-3 quick questions. So whoever is having can raise hand, and I request Dr. Satish to please take the questions from the audiences if there is any.
Archana,
yes, sir. Yes, sir.
I think this is a memorial workshop and time is tight.
Okay,
so
okay, sir.
I think it's better not to have a question, but people can send the questions, and
Okay.
we can pass on to the speaker, and they can respond in writing later.
Okay,
Yeah,
okay.
please, you can send me directly by email as well. I mean, these days we're all connected.
Okay, okay, sir. Yeah, so
Thank you very much.
Thank you, sir.
Otherwise, we cannot manage the time.
Okay, okay, sir. Yeah, we will do so. So whoever is having question, they can directly take it from Professor Arjun's email or through President EMASI, Professor Srivastav as well. So we will go ahead for the next speaker. I again thanks Professor Arjun. Now we have next distinguished speaker, Professor Andras E. Vladar. He is a project leader in the Microsystems and Nanotechnology Division in the Physical Measurement Laboratory. His current research interests are computational ACM, developing ACM methods to make atomic level quantitative measurements possible. He has expertise in nanometer scale scanning electron microscopy, atomic resolution, 3-dimensional measurements of particles, and so on. He is having more than 100 papers with very high citations. He will be delivering talk on the bright future of electron microscopy. I invite Professor Andras E. Vlada. Sir, please start your lecture, sir. Thank you.
Thank you very much. So please help me which way I can share my screen, or you run it. Either way, it works with me.
So I think it has been shared from our side, and
very good, excellent.
Yeah.
So then I will attempt to talk a little bit about the future of electron microscopy. To some, the TEM, STEM, and also mostly STM, but they share a lot of things, especially about what the future can bring. So first, I would like to express my gratitude, and I'm really honored to be here today and tell some of my thoughts about electron microscopy. And I wish those things that I'm presenting here and many others will come about in the future and will make electron microscopy much better to serve the advancement of science and technology. So get the first slide, please. So mankind has always been intrigued by large and small scale structures of nature. So first it was obviously light, microscope, telescopes, mirrors and lenses. But very soon we found out there are limits to these things. So about 50 years after the discovery of the electron, focusing, deflection, and so on by electron optics became possible. So did high magnification imaging. So in 1932, were the first electron microscope images got published, and then just a year later, at that time, unprecedented super high magnification image was published. So in the 1950s, there were all kinds of problems, understandably, from emission problems, control of the electronics. This was time of electron tubes, contamination, vibration, drift, and all kinds of things. So most of these problems are still around to some extent, but much smaller extent. So, but the point really is that tremendous and really unbelievable improvements happened in electron microscopy, serving a lot of other science and technology in the meantime. And the story is still far from its end. Next slide, please. So here is just a brief history, seeing on the left side the first practical transmission electron microscope from the 30s, and some things that are notable events that happened in the 40s, 50s, 60s, and so on. So you can see that this is a gradual but tremendous improvement in almost every regard. Electrons, focused electrons, or electron manipulation, electron beam manipulation can bring us. So there were improvements in almost every regard. The resolution improved significantly. Currently, it's under 50 picometer. People reported being able to see 47 picometer lattice structure of germanium and so on. And then the SEM scan electron microscope and OJ microscopes came somewhat later. You can see that the resolution is always lagging somewhat behind. For some of it, there are physics reasons, but for many other things, it's engineering reasons still. So you can see that currently we have definitely under 1 nanometer resolution, and even at 1 kilo electron volt landing energy. So what this is leading to now is that the SEM is taking over work from TEMs and STEMs, partly for physics reasons. But that little green dot shows that also what happened in the meantime from relatively inexpensive instruments to more and more and more. Today, it's not unusual that over $2 million or even more is one instrument. Some of the high-end instruments can be tremendously much more expensive, especially if you fold in the laboratories and so on. So these are not cheap things to run. Next slide, please. So I hunted down this photo from the internet, and you can see that this is something that was a work of true visionary, and it is obviously not just him, but a team of people, as we heard, put together this instrument. And the next slide shows that every single part that is needed for a modern TEM is there, obviously. So we have the high voltage, the electron gun, the condenser lens, the sample and the stage to manipulate the sample, the objective lens, projection lens, observation camera, the vacuum system. Earlier photos showed some of the guts of the instrument, pumps and other things. Keep in mind that these times pumps were, say, mercury pumps and all kinds of things. So just the fact alone that they've been able to publish images with it is just simply fascinating. Next slide, please. So what can be done with electron microscopes? Obviously imaging. So the resolution went down to atomic levels. We can do 3D, we can show molecules. You know, just recently Nobel prizes went to a team of electron microscopists and other people who made it possible to directly determine the structure of molecules, partly through the use of cryo-electron microscopy. Environmental, we have massively parallel beams, ultra fast. So it just goes on and on. The human ingenuity is just doing amazing job in electron microscopy. Obviously, it's not just simple imaging that is possible, but spectroscopy, finding chemical composition, electronic state, spatial and energy resolution down to atomic levels or sub or close to a cubic nanometer, depending on what it is. And of course, diffraction, crystal structures, and all kinds of things, seeing atoms, atomic structures, all those are absolutely important for advancing science, especially in the nanoscale. The next one, I would like to say a little bit about ultra low voltage SEM. This is the time when we are getting away a little bit from the traditional high voltage operation whenever it is important, and it is in many regards. I will talk about this a little bit later. Ultra high cleanliness, meaning we would like to operate the instrument in a way that we have the sample and the electrons, and that's it, nothing really else. And if possible, not in ultra high vacuum, because that's very expensive. So drift compensation is one of the critical parts, because we essentially want to keep the sample motionless in a few 10 picometer levels, which is absolutely not trivial, especially in the case of an SEM, but even for TEM is a challenge. Model-based measurements, which essentially entail use of physics in the interpretation of the measured data, advanced image processing, all kind of advancement in image processing can be and needed to be applied to electron microscopy. So the point is that electron microscopy is key to hundreds of billions of dollars per year production, from integrated circuits to nano to batteries to bio and so on. So it is absolutely important to keep these images performing really well and further improve them. So essentially, electron microscopy is indispensable to the advancement of science and mankind in general. Next slide, please. So obviously there are limits. There are physics limits. There are theoretical limits. Noise obviously is one, contrast to noise ratio. Confidence in the results in some of the highest end measurements. The confidence statements started to show up, which showing that now we are approaching the limit. So sample resilience is obviously another important thing, and that's why low energy operation in electron microscopy is becoming important, because much less problem to measure the same thing with much lower energy electrons if possible. So and that little summary there shows that what wavelengths the electrons have if the energy is say 1 or 10 or 100 electron volt. Also, you can see that compared to so the velocity compared to the speed of light is also growing as the energy grows, which has consequences both for measurements and for engineering purposes and interpretation of the data. So one limit is obviously the expense. So the manufacturers are in the business of making profit, not in the business of making the best possible electron microscopes, otherwise they would die out. But it's important that we tell them that what we would like to get from the microscopes. So as long as we put up, for example, badly contaminated systems or high-end electron microscopes, which are skimpy or not particularly well equipped for the latest and very powerful image processing systems, then it's partly our fault. We have to tell them, hey guys, put it in. So it is possible, but again, it needs to be a good cooperation and probably a better cooperation than we have today. So another limit is that do we actually need that information and for how much? You know, that these instruments are expensive. How to organize their work is becoming very important. It's not inconceivable, especially in the age of internet meetings and others, that remote operation, sending samples to an instrument and running them in 2-3 shifts. You know, you can have a sample in the night from India running on a high-end microscope somewhere, wherever it sits. It doesn't really matter. Samples can be sent relatively quickly. So luckily, there are still unemployed fields of electron microscopy to conquer, discover, and take advantage of. Just to mention a couple, generally, especially low energy, electron spectroscopy, so the energy of the electrons flying out and coming out of the sample, the trajectories, 2D detectors, complex detector system above and under the sample when we are working in STEM mode. There are a lot of things to add, stability of the sample, and so on. So we'll show some examples what we still need to work on and make things better. So key is that better engineering and design ideas and new solutions will make the future electron microscopes even better, and they will perform at unprecedented levels. Next slide, please. So, of course,
Hello, Professor Andreas. You are not audible. Hello. Hello. Hello, Professor Andras. Dr. Satish, can you hear?
Yeah, I'm just contacting him.
Yeah. Please, thank you.
Yeah, I don't know what's going on because it does not allow me to launch the meeting.
Okay.
I think probably if he reconnects himself, that would be better. Disconnect and then reconnect. Satish?
Dr. Satish?
Yeah, professor has disconnected, so he has to reconnect.
Yeah.
Yes.
He has already disconnected. Yeah.
Okay.
Oh, yes. I am discussing it. Yes, sir.
Okay.
Yes. Professor Andras?
Yes, I am here trying to
Okay.
troubleshoot on my end what could be the problem because the screen disappeared.
Okay. Sir. I think you can.
Can disconnect and then reconnect.
Dr. Satish, please resend the link to him, to sir, and so that sir can click on the link and rejoin. It will be easy for sir.
Yes, sir. Can you like disconnect and connect again using the link, sir?
Sorry,
Naren,
Yes, sir.
can you see Professor Andras and you can log out him because he is not seeing that
No,
live.
actually, he has already logged out from here.
But
Sir has
he's
already logged out, so he can click on the link and then again he can enter his name and then ID and password.
no, but he is still able to hear us. All the things we are speaking.
1 minute.
I can also hear us. Whatever we are speaking.
Okay, but professor is not there in the list. In the participants list, professor has not yet rejoined.
Okay.
So you ask him to rejoin and then
Yes. Professor Andras? Sir, can you just click the link again? It might able to.
Satish, please telephone him.
Sir, I just had discussion over telephone only.
Okay.
Because what happened is that his live Zoom screen is gone completely, but somehow on background it is still connected. So he was not able to reconnect or disconnect as well.
So I think sir can restart his system.
Yeah, he will restart the system and connect again after 15 minutes. We can continue with the next talk.
So, sir, should we stop this one and start another, Professor Carlos? Stop.
Yeah, if it is going to take time, then we can start. And once Professor Carlos' presentation is over, then we can request Professor Andras to reconnect and start.
Okay, sir. So, yeah.
So do you want me to present now?
Yeah, I will. Yes, sir. Welcome, sir. I will just briefly introduce you, sir, to the audiences, and then you can start. Yeah. So, Professor Carlo is a full professor of physics of matter at Politecnico di Milano, Department of Energy, Italy. He holds a master degree in electronic engineering and PhD in materials engineering. He has expertise in nanostructured material, metal oxides, carbon-based nanomaterials, Raman scattering, and so on. He has published more than 100 papers, and also he is coordinating Explore project, which is focusing on the potential of novel forms of carbon with an application-oriented approach. He will be delivering talk on exploring new materials from carbine to 2D carbon beyond graphene. It's really it's honor to you to have you here, sir. Please go ahead, Professor Carlo.
Okay, thank you very much. I hope you can hear me and also see the presentation. And first of all, I'm very happy to be here. I'm honored, and I would like to thank the organizers for inviting me and giving me this opportunity to present what we did about carbon nanostructures. So today I'd like to talk about not so famous form or known form of carbon, a little bit exotic, but with appealing properties. And so I will talk about linear carbon nanostructures to then pass to the possibility to use this linear nanostructure to produce two-dimensional carbon structures, a little bit different from graphene, but of course sharing the same element. So first of all, okay, of course I would have preferred to be there with you, but it's not possible due to the the COVID restrictions. So I'm here now, so in Milan, Italy, north of Italy, and I work at Politecnico di Milano, that is a technical university. It was founded in 1863. Not very old actually, because in Italy we have the oldest universities, so Polytechnic is quite young in this context. We have about 50,000 students only dealing with engineering, architecture, and design, and we according to university rankings, we are in the top 10 university in Europe in the subject of engineering and technology. I work at the Micro and Nanostructure Materials Laboratory, the NanoLab, in this building, and part of the Department of Energy. And we are a group of 8 professors and up to about 30, 35 people, young people working in the lab. So master thesis students, PhD students, postdocs, and technicians. So I start by just talking about the need for the advancement of technology. So in many different technological fields, we need many advancements, and here you can see some keywords. So, for example, low cost, non-toxic components, easy processable processes, flexible materials, miniaturization of components. And so these are, of course, only some of the requirements you would like to have to make important innovation in technology. And based on this, of course, you need materials with specific properties. For example, you would like to have materials that are flexible, mechanically robust, with good, for example, charge or thermal transport, with, in some cases, with high effective surface, that can be, for example, transparent or optically active, that can be metallic or semiconducting, and, for example, with very small scale. And at the end, what you would like to have is the capability to control the properties, as also was nicely discussed by the previous speaker. And so you'd like to be able to tune the properties to be able to engineer a material to be then implemented in specific applications. So if you go back, this is to say that to have improvement in technology, we need new materials or materials with engineered properties. And one example of this is carbon, because of course you know that carbon is employed in many technological applications, starting from, for example, electronics, then in composite materials. This one is the Lamborghini supercar. This is called the sixth element because it's made of graphite composites. Or some years ago, the Gillette produced razor blade covered by diamond-like carbon to improve the performances of the cutting edge. And then also diamond or synthetic diamond is used in, for example, detectors for nuclear applications. And also recently, as you can see here, graphene has been used in many different applications, but also to produce anti-COVID masks. This one, for example, is coming from an Italian brand that is producing graphene nanoplatelets near Milan. So, so carbon is very used and widely used in technological applications. And one of the reasons is that carbon is a versatile material, so it's able to produce different structures, including nanostructures, as you know. And but starting from the solid case, you know, you can have graphite and diamond that are completely different materials from the point of view of their properties, but still they are made by carbon. And so you can you can explain this based on the capability of carbon atom to hybridize its electronic orbitals in 3 different ways. So, you know, sp3, sp2, and sp. sp3 hybridization is able to make a sort of 3-dimensional organization in the space, and in the molecular scale, you have, for example, ethane, which is a molecule composed by 2 carbon atoms and 6 hydrogens, and is occupying the space, okay, in a quite uniform way, or as uniform as possible. And in the solid state, you know that you have the diamond structure that is a face-centered cubic structure with 2 atoms per unit cell, and the isotropic properties of diamond come from this kind of organization resulting from the hybridization of the carbon atoms. In addition to sp3, you can also have the possibility to have carbon in sp2 form, and this is a more planar organization, so in the plane with 120 degrees orientation in the plane. And for example, the corresponding molecule with 2 carbon atoms is ethylene, with 2 carbon atoms and now 4 hydrogen atoms, and is a planar molecule, okay? Now, if you go to the solid state case, you have graphite that is organized in a similar way. So you have the hexagonal planes that are very, very rigid, but the connection between the planes is very soft, is given by van der Waals interaction that are given by these p orbitals that are not hybridized in the sp2. And so, for example, you can explain some way the anisotropic properties of graphite, sorry, based on this kind of organization. So you have also sp. sp is linear, and so you have, for example, acetylene that is a linear molecule, now 2 carbon atoms and 2 hydrogen atoms. And one question could be, what about the solid form based on sp hybridization? So this is still today a question mark, but the scientists have looked for this kind of a material based on sp hybridized carbon for many years. So we have graphite on one side, diamond on the other, and speaking about carbon nanostructures, we can put them in between graphite and diamond. For example, of course, graphene is the direct example of graphite in the nano form, because you exfoliate graphite to have one single layer of hexagonal carbon plane. And if you rotate, and I mean you roll up a graphene layer, you can have carbon nanotubes, and then by for example, adding pentagons, you can have fullerenes, so the closed cage, with a little bit of sp3 in this sense, because you are distorting from the planar organization. But of course, in this situation, you also have the sp. So in a sort of ternary diagram in which you put sp, sp2, and sp3 hybridization, the question mark is here, but we can speak about the corresponding nanostructure based on sp hybridization. So one example is the carbine. Carbine, the name is not well defined, but we typically consider carbine the single chain of carbon atoms, ideal chain, that is one-dimensional. So in this case, you have a sort of wire, a carbon wire, that is infinitely long, and this represents, of course, the ultimate one-dimensional system based by carbon. And this is very interesting because it's a sort of a one-dimensional crystal. So from the point of view of theory, is very interesting, and is also a very good example for textbooks. For example, you can easily see that you can easily, I mean, understand the electronic properties, the band structure of this kind of one-dimensional crystals. And actually, if you look, if you think about the sp hybridization, you can see that you have indeed two possible organization of the atoms in this chain. One possibility is to have all double bonds, so double bonds, in a sort of equalized structure. So all the atoms are at the same distance. So the unit cell is one atom per unit cell. And you can easily see that this will lead to a metal, a one-dimensional metal. So with a half-filled conduction band. So this structure is called cumulin, and is predicted to be a metal. On the other case, you have the possibility to have an alternation of single, triple, and so on bonds in a sort of dimerized chain. Now you have two atoms per unit cell, and by solid-state physics reasoning, you can see that a gap will open here, and you will have a completely valence band, completely filled valence band, and a completely unfilled conduction band, giving rise to a semiconductor. So we have two possible structures, ideal structure, one leading to a metal and one that should be a semiconductor. Okay, and this could be quite interesting also for electronic applications, as I will show you later. Okay, so of course, based on this, these kind of systems were very appealing for theoreticians, and so based on theoretical predictions, you can see that the properties, the predicted properties, could be very, very appealing and interesting. For example, the extremely large Young modulus have been predicted up to 30 terapascal. That is that makes this material the hardest material ever. Also a huge specific surface predicted to be larger than 10,000 square meters per gram. That is 3 times the one of graphene, or something like that. A super high thermal conductivity, electromobility very high, similar or almost similar to the best for graphene, and also intense optical absorption. So based on these properties, these kind of systems are very interesting for making tunable or specific materials with tailored properties for applications. Of course, what I showed you up to now is the ideal case, so an infinite wire that is infinite long without any termination, and so it's not possible to have this kind of material in laboratory. So in experimentally available structures, you have to consider that the system must be finite, and so the termination at the end of the chain must be taken into account. So I here show you some possible structure that are experimentally available. This is, for example, these are very some possible structure. I will show you other with different termination. For example, very appealing the case of the chain terminated by graphene edges, and this is a very nice TM picture showing the single chain here that is connected to graphene edges. And another way to have this kind of system, for example, very easy to be for electron microscopy, for example, is this is the first work in 2003 showing the possibility to have a linear chain inside the core of a carbon nanotube. This is a multi-wall carbon nanotube. Here, if you count the number of lines, at a certain point, you see here that you have a single line in between here, the core, and this cannot represent a wall of the nanotube, but should be a carbon chain. And the previous case, so the linear chain between the graphene edges was produced in a very I mean, smart way, I would say. So by using the transmission electron microscope as a fabricating tool, so in a top-down approach, as you can see in these screenshots from this paper by the group of Jean. And so by removing carbon atoms from graphene, using the electron beam of the TM, they were able to finally get the linear chain connecting to graphene edges, like in this picture. And this is similar to the structure that could be seen here. The possibility to have the single chain inside carbon nanotubes is very appealing because carbon nanotubes are able to, in some way, protect the linear chain against the reorganization. And so in this way, it's possible to make very long chains, as was done by Leishi and his group. I want to show you here this example of a way to use the nanotube as a sort of reactor. So by putting short chains inside the nanotube, and then by a thermal treatment being able to produce the connection between the different short wires into a longer one. And with a similar process, Leishi in 2016 was able to show I would say the longest wire inside a carbon nanotube that is really approaching carbine, because they observed a wire 600 nanometer long, so composed by about 6,000 atoms, whose properties are no longer dependent on the size, and so this could really approach the property of the ideal case. Okay, now I just mentioned that the long chain is the very long chain is no more affected by the size, because this is an important property in fact. So finite chains are actually very interesting, because the properties depend on the termination and the size. So the number of carbon atoms composing the wire and what kind of terminal atom or functional group you put at the end. So for example, here you can see from theoretical predictions what is expected to happen to optical properties by changing the number of carbon atoms of a carbon atom wire terminated by hydrogen atoms at the ends. And so you see a very nice shift of the optical absorption towards the visible for increasing the length of the carbon atoms. And a structural parameter that is able to describe what happens is the bond length alternation, or BLA, or BLA, that is the average distance between one bond and the other one. So for example, in the polyene structure, so the alternated structure, this BLA is larger, while in the cumulin, the equalized structure with all double bonds should be ideally zero. But of course, in a real structure with terminations, as you can see here, the polyene has the BLA, the BLA at this level, okay, while in the cumulin is approaching zero, but is not exactly zero. This is because it's not ideal and infinite, but the termination plays a role. In the same way, the band gap in between these two, because ideally I showed you that one is semiconducting, the other one is metallic, but in real case, when it's finite, you have a band gap that is depending on the BLA value. So by decreasing the BLA, you decrease the band gap from semiconducting toward a zero band gap structure. So talking about the experimental available systems, these are some of the technique that I've been using since 2002 for the synthesis of this kind of materials. So one is a supersonic cluster beam deposition technique developed by Professor Milani at University of Milan. We have a very strong collaboration able to find out the presence of sp carbon in amorphous carbon structure rich in sp. Now we developed hard discharge techniques and pulse laser ablation techniques in liquid, able to produce short carbon atomic chains, carbon atomic wires. Another possibility is by means of pulse laser deposition in the presence of a background gas, or by collaborations, we have the possibility to have this kind of system by chemical synthesis that is very, very good in controlling, in finely controlling the termination. Of course, one problem for these systems that I also mentioned by talking about the wire inside carbon nanotubes is the stability, because these systems are mainly affected by degradation, and so the stability is very important if you want to then test or move to a material and its properties for possible applications. I want to show you here what we do. So we developed this is the hard discharge in liquid. This is the pulse laser ablation in liquid. Let me know if it's okay, it's working. So you can see the hard discharge between these graphite electrodes in a solvent. The solvent plays an important role for forming the terminations and the kind of structures. In the same way we do pulse laser deposition. You see here the laser shot that is focused on a graphite target in the presence of a solvent. In this way, again, by tuning the laser parameters and the type of solvent, you can tune the type of carbon atomic wires that you form. Okay, sorry, I stopped. The noise is not very nice. Then once you produce your samples in liquid, of course you want to see what's inside, and so we do liquid chromatography. So liquid chromatography based on the optical properties. I showed you that the optical properties are strongly related to the size. We are able to look at the different species present in the liquid and then also to separate them, and so to have the vials containing the different chains with different termination and length. One of the main characterization techniques for this kind of systems is Raman, and I was very glad to see in the introductory video about Dasgupta that he worked with Raman, and so I'm very happy to know this, because I didn't know actually. And so Raman is very sensitive to the local bond structure and organization. So, and you know, maybe that is very useful to know the number of layers you have in graphene, and is able to distinguish between graphite, graphene, fullerenes, diamond, and the carbon atomic wires have very peculiar features in a region that is not covered by all the other carbon nanostructure, that is in between, let's say, around 2000 wave numbers. And so Raman is very useful to distinguish and to observe the presence of this kind of structure. More than this, the Raman peak, the main peak, shifts with the length again, because the size is able to change the vibrational properties, and so by this shift we can also distinguish different structures. This is an example. You have on top isolated wires in which we see the main SP peak and also the termination, that is the phenyl, or in a mixture of sp2 and sp carbon, we can see the well-known DNG bands for sp2 amorphous carbon and sp. But more than this, we are able to distinguish and to observe the different chain length in the sample. For example, in this case, from the experimental spectrum here, with the presence of different lengths in many peaks, by DFT calculations of the vibrational features, we are able to distinguish the different contribution of the different lengths. This is, for example, for hydrogen terminated chains, for phenyl terminated, for ones terminated by two phenyls, and so on. So Raman is very useful to observe and understand what kind of material you have produced. And this is an example of what we do by pulse laser deposition in liquid in different solvents, including water. Depending on the solvent, we can see different yield of formation and even type of termination. For example, in acetonitrile, we can see have the formation of hydrogen terminated polyions. These are all single triple bond structures, or terminated by methyl groups, or terminated by cyano groups, CN, coming from the acetonitrile, so from the solvent. And these are all the length from 6 to, for example, 22 carbon atoms observed, and by comparing the experimental data with the theory, we are able to distinguish and recognize this kind of structure. What about stability? We looked at the stability of this kind of system. Of course, the stability depends on the length. So the shorter chains wires are more stable than the longer ones. So I would say that, for example, 8 and 10 carbon atoms is very, very stable, while, for example, the C20 is a little bit unstable. And also the solvent plays a role. For example, in water, the degradation is quite fast, while in organic solvents the stability is much longer. So to work on the stability, we try to develop a way to stabilize the systems, and one possibility is to embed the chains or the wires into a polymer. So we produce this nanocomposite in which the systems I showed you before have been embedded in polyvinyl alcohol polymer, and we got the cover page of Material Advances for this, and you can see that the stability with respect to the system in solution is very much improved. So up to almost 1 year, we can still see the signal coming from the carbon wires into the polymer. And we were also able, this work is in collaboration with Professor Bertarelli at Politecnico di Milano, and we were also able to produce nanofibers of polymer, including this kind of structures. You can have a random distribution of aligned fibers, and from this SEM image you can see that the diameter is of the order of 100, 200 nanometers. And again, by Raman spectroscopy, you can recognize by looking at, this is the polymer alone, this is the carbon atomic wire before the insertion, and in the nanocomposites you see both, so the polymer and the carbon wire. Stable systems are very useful. In fact, by collaborating with Rick Tikwinski in University of Edmonton in Canada, he sent us these very nice systems. These are cumulin-like systems, so double, 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 or almost double, 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 because the termination is affecting the structure. And these terminations are able to stabilize the system. They are very interesting because the optical absorption is in the visible, not in the UV. And you can see that by changing a couple of carbon atoms in the chain, you shift from yellow to dull red. Okay, and they are stable. They are stable when dried on a substrate, producing those very nice needle-like crystals, also very, very big, very, and also, of course, by Raman spectroscopy, we can follow and understand what kind of structure they are. And in this, for this material, we tested electronic applications. So in collaboration with Mario Caironi at Italian Institute of Technology, we were able to produce a field effect transistor in which the active material is the cumulin wire that I showed you before, deposited on interdigitated electrodes. So you can see here the covering is not very good, but it was the first proof of concept. You see here by optical microscopy the needle-like crystals I showed you in the electron microscopy image before. And as the first proof of concept, the transistor works quite well, and we are still improving the performances by engineering the process of the deposition process. I'd like to to move from linear systems to two-dimensional systems. And this is a sort of history of development of carbon nanostructure, Fullerene nanotube, graphene, of course. This is the very long polyene system produced by Rick Tikwinski in 2010. And starting from 2016, there was this report on the possibility to use linear precursors to form a two-dimensional network on a substrate. And this opens very new perspective. Okay, so because the idea is that, okay, you know graphene, but by playing, if you insert or include the sp carbon, you can have, for example, graphene, so a sort of mixture between linear and hexagonal structures, or by using longer parts, you have the graphdiene with double acetylenic bonds here. So these are sp2 two-dimensional crystals that have a tunable porosity, and they can be semiconducting or semi-metal. So this is very appealing for applications, of course. And again, theoreticians were very interested by this. And for example, in 2012, the group of Malco reported this, showing the presence of Dirac cones in this alpha graphene. And in the same way, this is the, for example, the gamma graphdiene, one possible structure. This, for example, is semiconducting, and also you can predict the Raman spectra. Of course, by confinement in graphdiene nanoribbons, you can play with confinement to tune the band gap, for example, like this, in armchair or zigzag structures made by graphdiene, and also the Raman should be able to distinguish between the different structures. And in particular, for example, this the smallest nano ribbon, we were able to experimentally produce something similar by the so-called on-surface synthesis. So by collaborating with the group of Wei Xu in Shanghai, starting from this molecular precursor, if you evaporate this with bromine atoms on gold, you have the release of the bromine atoms, and gold is replacing bromine and form this kind of metal organic structure. If you anneal the system, you can have the removal of gold and have a homocoupling of the carbon atoms here, and have a very long sort of sp2 polymer. Okay, so we did this by and investigated by scanning tunnel microscopy and by Raman spectroscopy. These are images of this process. This is the bare and clean gold one-on-one surface. When you evaporate, you see the formation of the molecular chains, and by annealing, you have a sort of modification because of the occurrence of the removal of the gold atoms. And here we follow this because at low temperature, I mean room temperature, we see the gold in between the chains, and this is theory. By increasing the temperature, is not very clear, but the bright protrusion here is absent, and this is the theoretical prediction. So we move from these metal organic chains to all carbon chains. We did the same even in collaboration with Veixu, with this kind of precursor, able to produce two-dimensional network. And so in the same way, by the evaporating, you have a release of the bromine, and gold is catalyzing this kind of structures. Then if you anneal, you should have this kind of structure. So this is what we observe by increasing the temperature. Of course, we observe the release of the gold atoms, but also some distortion of the structure. By comparing theoretical simulations with what we observe, this is the metal organic system, while in this case we have something moving towards the homocoupled network. By theoretical simulation, this is very interesting because the system is affected by the presence of gold, and so with respect to the freestanding system, you have a change of the band gap or a metallic behavior with respect to the freestanding case. So again, the presence of gold can be used to tune the properties of this kind of materials. We did, and this is also reflected in the vibrational properties. For example, here by Raman, you should expect this, these are simulations, you should expect this change when you have the system on gold or freestanding. We observe the system on gold, of course, and the observation is supported by the theoretical data. So I think that I have to conclude, yes. So I try to quite quickly show you or tell you that carbon atomic wires have tunable properties that make them quite appealing for future applications. Of course, a lot of work must be done to improve the stability of these systems. When you achieve stable carbon wires, you can make a sort of material and you can test it in technological application, as I showed you for the field effect transistor realization. And then also you can move from 1D to 2D and form ideally a new class of two-dimensional carbon structures that are very appealing from theoretical predictions and are experimentally available, but with still some work to be done to have them ready for testing applications. So I want to conclude by acknowledging all the people working on this work, so all the team at Nanolab, collaborators at Polimi, and other collaborators that I also mentioned in this presentation, and also the funding from the European Research Council, and of course all of you for your kind attention. Thank you very much.
Thank you so much, Professor Carlo, for your interesting and knowledgeable talk on the carbon wire synthesis, their properties, and challenges associated with them. We really thank you for your time. However, because of the time constant, we will not be taking questions. If anyone is having questions, they may contact to Professor Carlo's email directly.
Yes,
thanks
of course.
again. Thanks
okay.
again. Okay,
thank you.
So I think Professor Andres has joined us back. Professor Andres, are you there?
Yes, I am. Can you hear me?
Yes, yes, we can hear you, sir. Yeah.
Okay, very good.
So,
please put the presentation back. Probably that slide that I don't know what happened, but we just got disconnected and it couldn't reestablish the connection.
Yeah.
So we've been. So may I go on?
Oh, yeah, please go ahead.
Okay. So there are obviously practical limits to electron microscopy. Is even the most expensive microscopes could perform much worse than they are able or should be capable of. So the environmental laboratory, whatever it is, and if needed, could be improved many times. The problems arrive from somewhere else. Existing instruments can significantly improve their performance by implementing a few procedures and regularly check the performance. One is the focusing ability, and including some aberration correction one way or another, choosing the best parameters for a certain task. Take care of the drift, which is both the stage and the beam, meaning the electron beam does not end up at that sub-nanometer spot where we want it to be. Contamination that could come from the instrument and the sample, which means material there that we don't want on the surface. We would like to have just the sample and the electrons, and preferably without ultra high vacuum, because that's very expensive, but in some cases we have to do that. So optimization of this instrument can take or can result in excellent quality images. And the measurements provide much better information, closer to reality, more reliable traceability, and other things for standards purposes can be established. And but this can be done these days down to a few or a couple of single items. Next slide, please. So here is a bunch of things combined on it. I'm not going to go through all of them. If you are interested, you can dive into the details. So there are electrons coming above the sample and under the sample. There are some requirements here for stability and for beam steering as well, and for the detectors, and then what kind of contrast we might have. So it's a lot of things that electron microscopes could work with and do work with, and to choose the proper parameters is absolutely important. Next slide, please. So TEMs, transmission electron microscope, scan electron microscope, and scanning transmission electron microscope have a lot in common. The SEMs generally are years behind the TEMs in many respects, but they started to catch up. So as high sub-nanometer spatial resolution on the SEMs becoming available, measurement can be optimized better, take advantage of the more optimal lower landing energy. So many of the measurements that currently are done or in the past been done on traditional TEMs and STMs, the SEMs can take over because the lower landing energy is allowing that. So 0.2 nanometer is the best current resolution, and for EELs that can be added at low energy, 30 kilovolt or under, elemental mapping, 0.4 EV best resolution. And so these are very good advancement that make the SEMs, especially in STEM mode, particularly powerful. So the key part is that modeling has improved. You know, modeling has been a part of life in TEM and STEMs since a very long time, especially for crystal and other structures, but not that much for crystal structures yet, but obviously that's also doable. But for other signal modeling down to 50 EV is becoming a very powerful tool for SEM measurement optimization and interpretation of the measured data. So allowing sub 10 nanometer 3D structure measurements with a few atoms worth of accuracy, matching the results of X-ray scatterometry or TEM. So these are very, very powerful things. The very, very low energy though, under 50 EV, the primary electrons start to behave like any other electrons. There is no, that's also a different, somewhat different realm of modeling that is not developed. So that's one area of improving. So high performance on-the-fly drift composition methods are now available or becoming available for TMs and SEMs. So that allowing for stability at sub-nanometer levels, which is critical for many of those results that you've seen already. So as you know, the future of electron microscopy is indeed bright. Next slide, please. So I am going to show a few examples that where further improvements are possible. One of them is the instrumentation improvement, which is unusual design that you can see on the screen by Zeiss. This allows, you can see that on the right side, there's an electron source, goes into a beam separator circuitry. Those are cores, those orangey brown structures. There's an electron mirror, and then the electrons are channeled into the lens system, the electron optical system, and hit the sample, come back and end up in the electron spectrometer. So this is obviously a very different design from what we usually see in SEMs or TMs, but it comes with excellent resolution, sub 0.6 nanometer resolution at 100 EV at 30 picoamp beam current. So aberrations are significantly improved at low energy operation. Chromatic aberration is one of the problems. So either someone chooses an electron optical or electron delivery system like this, uses a trick that FEI uses, for example, for low energy operation, when right at the vein out, when the electrons fly out of the cathode, they move the beam to the side and use only a small portion of the beam on the skirt where the energy variation is much smaller. If you think about it in an SEM, TMs are similar in this regard. We throw away every electron but 1 out of a million. So the emission is in the nanoamp region, and the high resolution imaging current is in the picoamp region. But in this case, for low energy operation, they don't do that. They had to design and reconfigure the system to be able to minimize chromatic aberration this way. They use a thermally assisted electron source. So then the point is that this is one of the possibilities, novel designs. Next slide, please. Even if you don't have that kind of super duper instrument, but you care about your instrument's performance, if you regularly check it, it will lead to a significant improvement. What you can see here is a software called Image from FEI. FEI users get it. Others can use either this David Joyce smart algorithm. There is a with NIH ImageJ. Then you can download that little macro, or take advantage of the ISO procedure, which is a link here, a new version coming soon. So you can see that these red bar results show that what performance you can get from an instrument that the specification is better than 1 nanometer. This is at 15 kV. You can see that it's significantly better than 1 nanometer resolution is possible. We'll talk a little bit later about how important this is. Next slide, please. Next slide, please. Okay, very good. So contamination ruins the resolution and the sample. I don't want to go too much into this, just shows that it could be horrendously bad. And this is a case when it is good, so you will not have contamination anymore. In the case of silicon, due to the vacuum system working in the 10⁻⁶, 10⁻⁷ range. You will have water on the surface, which will oxidize under electron beam irradiation. That's where the brightening, actual brightening happens, because you make this silicon oxide, the native silicon oxide, thicker. So this is especially at low KV, because you have a lot of secondary electrons close to the surface or at the surface at low energies. So it is possible to have an SEM so clean that for a month, you don't need to clean it again, and you can dwell on the sample as long as you wish. If you want hours, you will not have any carbonaceous contamination. The next slide, please. Next slide, please. Very good. So this is, just please go back one, somehow I jumped two. That's about the sample. This was a sample that has been in storage, not used for years. The first image that you see is on the upper left. But if you dwell on the sample for 10 minutes, as twice as high magnification, in this case, 200,000 times magnification at 1 kilowatt accelerating voltage, you will see a really ugly pattern forming due to the sample problem. The sample had contamination precursor molecules in it. The SEM itself was clean. So after cleaning the sample in hydrogen plasma, obviously in a golden carbon sample, you will not clean in oxygen because it will just crumble. You can see that after cleaning, the first image looks a little bit different, but after 10 minutes, you don't see that ugly contamination because the precursor molecules were largely removed from the sample. Next slide, please. So what you see here is that the center portion of the same image. It's a digital magnification to show things better. This is an evidence that electron irradiation can improve the contamination situation. You can see that the center portion that got irradiated at about 40 sometimes the dose of the usual 1 minute image, small features started to show better. And if you go back to the earlier image, the very first one, you will see some of them, but not many of them. So that insert shows that if on a 30 nanometer size gold particle on silicon chip sample, and you take an image and in a clean, everything is clean, the sample is clean and the instrument is clean, you evaluate the so-called resolution with this software FEI image or Thermo Fisher image that I showed earlier. There, take another image and another image, you get improvement in resolution, about 5% further improvement, because the electron irradiation removes very tiny amounts of leftover material. So you end up with a cleaner surface. Why important this is? Because there's about 1.8% difference in particle size measurements due to this. So then if you measure at the beginning and measure later after the electron irradiation of the sample, you will measure them smaller. Obviously, that's closer to reality. Next slide, please. So here are some instruments that can be used to clean the microscope. Both TEM, SEM can be cleaned with versions of these. One is plasma, low energy, 10 to 100 watt oxygen, hydrogen, or for even more sensitive samples, helium plasma could be the way. But there is a new one here, which is particularly remarkable. This is called Sparkle EC, which uses an electron flood. So you can see the little control unit, that blue box. and the head, which essentially is a tungsten filament that emits low energy electrons and cleans the instrument over time, and also cleans the sample surface. As you saw, electron irradiation has a cleaning effect. So this is a lot more powerful than just this small few 10 picoamp electron beam. The other advantage of this works in high or ultra high vacuum, and that makes the removal even faster. So even much lower energy, it's about 4 watts that it go into it. The cleaning rate is quite sufficient. So again, there are many applications when not really ultra high vacuum is what we need, but ultra high cleanliness. So next slide, please. Here is some explanation or sort of little idea that what do we mean by that. So if you have high vacuum and a dirty SEM with a dirty sample, you will have that ugly deposition that you can see on the left. Even just one image can get darker and so on. If the SEM is cleaner, but the sample is not really clean yet, then you still have something. The center may stay clean because the electron cleaning and deposition can overwhelm each other. Next one is when you work in ultra high vacuum in an ultra clean SEM. In the case of silicon, you will end up with no carbon deposition, but some oxidation. And if you have, because you still have water present, it's part of the physics of vacuum. If you go for ultra high vacuum, ultra clean SEM, then you will have no oxidation. So what we are trying to do is manage and engineer the ultra high vacuum, the performance to achieve the performance that you can get in the ultra high vacuum, ultra clean SEM imaging in high vacuum. So how we try to do that? We use UV laser and an infra laser to manage the surface during the measurement electron imaging as much as possible. Obviously, you cannot do everything with that. So that actually showed some remarkable preliminary results. Later we'll publish paper on that. So again, it is very important, especially for these samples that we've seen today for both presentations, to measure the sample, not the sample with an unknown amount of material that is interfering with those atomically important structures. So that is a very significant improvement and possibility to get much, much better results. You know, we know very well that even a monomolecular layer of monoatomic layer of material on pure metals will change significantly the intensity and the energy distribution of the secondary electrons that come out of the sample. Next slide, please. So this is just a simple thing to set the scale right. So whenever you are quoting some result, you would know that that is indeed proper. 2 possibilities at least, and we have this software available for anyone, and also there's an ISO procedure that one can follow. It makes sense to get that right because sometimes misleading results can occur. Next slide, please. So when you are measuring, it's important that your lab is all right. For the time of the measurement, just turn off sound and everything, because at nanoscale, you will see that this, as you can see that the computer speaker on and off, those little jaggedy edges are much worse when the sound is on. Next slide, please. So obviously, we and that the lab is important. You can see that if this is just an example from NIST so-called advanced metrology laboratory. The building was designed to have very good properties, both for vibration, electromagnetic noise, and other parameters. So you can see that especially labs done in the underground part of these 5 buildings, those are particularly useful for really high resolution measurements. Next slide, please. As just a simple example, if you use a chair which has a steel backing, that you may end up image distortion like this, because the DC magnetic field does not really interfere with the microscope imaging. But when you move that magnetic field by just changing the distribution of it, by moving the chair back and forth, you may end up an image like this, a distorted results. Obviously, this is just an example to show that external electromagnetic fields, even if the instruments are designed to have good shielding against these things, could ruin your results, especially at the nanoscale. Next. Here is something that the cooling, usually instruments, due to the high strength fields used in the lenses, require some kind of cooling. So depending on what your water source is and what your pump is, your resolution performance could depend. You can see on the left is an old pump. We found there is a problem with it, and we replaced with a new pump, but that was working in the summer when the city water was too warm. But when you in the winter switch to city water, it was even better. Now we are using a recirculative cooling system, and we'll show some results on that, why this is so important. Go to the next slide, please. So you can see that we had a chiller which had temperature variation quite a bit, and we replaced it with another one. And what we do on our instrument is we overcool the water, and we have the cooling water. And we have a local little heater that keeps the temperature, because we measure the ingoing and outgoing coolant temperature and get a much better temperature regulation, because drifts and other problems occurring when you heat up or cool down your electro-optical column components, depending on how your chiller works. Next slide, please. So here is an evidence that the pump, the chiller pump, which circulates the coolant, has or could have a significant effect on the performance of your instrument. With the laser interferometer, which one of our SEM is, see evidence that there is about almost 2 nanometer worth of wiggle that we found at the Fourier shows 120 hertz. This is coming from the pump, which was shaking the coolant as it was pumping the cooling water through the system. So we had to replace this, obviously, because this essentially just ruins our resolution. And we did get improvement due to that. Next slide, please. So here is some evidence of what's going on. It's not too surprising that the sample stage is not stationary. This is true for TMs, but to a much smaller extent. That makes it possible to get those very good quality images in the TM. Even there, drift and vibration and others are significant problems. And there are some new methods that through image processing or advanced imaging and fast acquisition, they can do some things better. So what you can see that this moving pattern, the beam was supposed to be stationary wherever that little red dot is. But what you are seeing here moving up and down, and then this film strip at the lower part, we plotted that where actually the stage was. So these are millions of data points. The laser is very fast and has 38 picometer resolution. Shows that most of the time, the beam, this was supposedly a stationary sample, is at the two extremes. So it's like almost like a pendulum motion. So the stage moves in one direction. Same thing is true for the electron beam, and the will do you the favor to follow each other is zero. So you end up in a compound similar problem. The frequencies and the amplitudes vary, but the nature does not, meaning most of the time, the beam is at the stage is at the two extremes, just like a pendulum. It moves into one direction, slows down and stops, and then speeds up and moves. So it stays the shortest time exactly where we want it to be. So that's obviously not particularly good. And there are also motions, not just in one, but in all three directions. I don't know if you can hear that or not, but if you later see this presentation, click on that little thing. There is a play button shows up if everything is all right. What you can hear then is somebody was standing next to the SEM and counting 1, 2, 3, 4, and so on. And the laser interferometer picked that up. So that if that was possible, then it means that your sample stage or SEM is shaking with that acoustic impact that your voice creates. So for the time of your measurement, stay quiet. Next slide, please.
Actually, Professor Andres, while
Yes.
clicking that audio, it has got stuck. The presentation.
Okay.
So yeah, soon it will coming to next slide.
Yeah, I never delivered this talk through Zoom. What I recommend you to do is hit escape, so you will go back to the regular slide view and advance to the next slide.
Yeah, just a moment. Yeah, my colleague is doing that.
Okay. So if you advance to the next slide and then hit F5, it should be okay. Yeah.
Okay.
All right, very good. So then this is just about something that fast imaging is better because you can compensate for these motions. So you can see on the left, fast image, it was only 11 milliseconds to get that image frame. But if you acquire like 70 of them and add them together, what most SEMs do, then you end up with a blue. But if you use a two-dimensional Fourier-based lining the images up, these fast individual noisy images, you get the image which is on the right, obviously much faster. Similar solution for the TEM is available even as an aftermarket solution from prototypes. They just showed very nice images when you do a heating in your TEM or STEM, and then instead of waiting for a long time or doing all kinds of tricks, the software solution keeps everything in stable and in focus. So you can see at the bottom that we plotted that what the stage was doing over time. If you can do that, and also allows you to check whether the stage performance is all right. So then here's an example showing down to very, very low on the right, very signal to noise ratio, very noisy images can be still added together with sub-pixel accuracy to allow this Fourier imaging. Next slide, please. There's a software available from NIST. You can see it at the bottom from where you can download this. And you may need to play a little bit with it, but it works very well. I highly recommend it. And in some SCMs are already having this, the higher end new SCMs have this built in. Next slide, please. So then comes that, okay, so we have an instrument which is not contaminating and all kind of good things already being done to it. What can we do otherwise? One thing for sure is do not acquire information that you either already know or you are not interested in. So for example, if you want to measure the width of the line in the vertical and horizontal direction, is no point to acquire the whole image, throw away a lot of data and just use whatever you want, or the image next to it, choose only the area where the information you are looking for is. And better yet, acquire information the fastest way. So obviously, this means that we have to do better than the traditional scanning method. Next slide, please. Yeah, so then the traditional forced raster scanning is wasteful because what we do is we acquire an image first, save it, and then pick the area of interest, and we throw away the rest. So, which could be quite a lot. So instead of that, we should use methods in which we put the beam exactly where it needs to be. It's not trivial in engineering, but it's doable. Therefore, what you can do, you quickly acquire a relatively noisy low-dose image of the whole field, which will allow you to figure out where exactly your region of interest is. You can add to this that don't acquire information where too much where the signal is large. You don't have to dwell equally on those pixels, because when you have a very strong signal, you know very well, again, don't acquire information that you already know. And apply sophisticated noise reduction, sparsity, deep learning based removal of noise, and also use so-called in-painting method to generate an image suitable to finding the area of interest, and then acquire the needed information only. So here on the right, there is an example to show that out of how sparse, how noisy images of what you can see as input, without prior knowledge, meaning you don't know how the sample could look like. You couldn't teach your algorithm to figure out. You can reconstruct the center image, but if you have prior knowledge, you can further improve that. So it means that tremendous improvement can be achieved if you use technology, sophisticated image processing that is already available. Clearly, when you have instruments, $2-3 million, you don't want to wait too long. Moreover, many times the sample itself is not that resilient. So be able to do the absolute minimum interaction to gain the information we are looking for is very important. And it is possible much better than what's mostly implemented today. Next slide, please. So here is just an example. I would like to ask you to go through the first then the next 4 slides quickly. This is images taken at different magnification, different samples. Next slide, next slide. So what you can see here that, just step back one, please, because you went a little too fast. It's slow apparently over the internet. Yeah. So what happens is that if you recall that these images were moving while the sample was not moving, is not supposed to move. An image and then another image without changing anything, just retaking it, supposed to be different random noise only, but that's not the case, especially in low speed imaging, which is the traditional imaging in the so-called slow scan image acquisition, which is generally a bad idea. So if you go for the next slides and try to go through them one by one, you will see that on the left is the traditional imaging, and on the right is this Fourier-based stuff. Next slide, please. Next slide. Next. It will be altogether 16 of them added together. And yes, thank you. You can see that the traditional image gets very blurry. And the next slide shows that the traditional imaging does you the favor to keep your numbers and letter blurs your image. And the proper imaging method will not do that. It keeps your image sharp. And in exchange, if you do apply it to the full image, then it makes your letters and stuff blurry, but obviously you don't have to do that. Next slide, please. Yeah, so this is what shows that what the results are. Next one. So here we apply the same technique, and this is just an illustration because we did not use in the lining the images up the whole Fourier of the letters and numbers at the bottom. This allows for roughly 10, 11, 12 nanometer wide integrated circuit lines, images to be acquired so that they are very good quality. Otherwise, you will not be able to get this quality, that fidelity. Next slide, please. So once you have your images acquired with very good fidelity, then you can do what we've done, model-based measurement, in which we generate a library of possible waveforms, knowing that what the structure might be, and then figuring out locally that which one is the best fit. You can do a 3-dimensional reconstruction based on the SEM image at a couple of atoms worth of accuracy and matching the TM results. So you can see here the TM results, which actually show the things that, you know, this is a 10 nanometer, 12 nanometer structure very well. Some discrepancies always arise because exactly where the TM results came, and we'll talk a little bit about that, and the SEM results came somewhat different. But the key with the SEM stuff, this is non-destructive. You can keep your sample, you can measure it at very high accuracy. Next slide, please. So a little bit about this 10 nanometer structure. So on the right, you see some faint structures of the crystal lattices show up. But the question really is that where exactly the sample is. So but this is by no means trivial. First of all, the number of atoms that generate a signal is very small. And it's not to say that we don't have sensitivity to even a monoatomic layer to things, we do. But whenever it comes to determination of size and shape, the things are not trivial at all. So one thing is obvious, that a small number of atoms cannot generate strong signals quickly. So then complete optimization of the measurement process is indispensable. Next slide, please. So here are some examples for 3D measurements. These are 60 nanometer size gold particles with the typical hexagonal, triangular, or pentaprismical and other structures. Next one, please. These are 30 nanometer ones, also showing these typical objects, some hexagonal, triangle, some standing on the edge and so on. Next one. These are 10 nanometer size structures. We improved things in the meantime, but why I'm bringing this in, that I'm playing in that moving little window, some of these, like 8 or 10 of them, showing that even within those 10 nanometer structures, we can see 2-3 nanometer areas which are brighter than the other. Why? Because there are more gold atoms are in that direction in those structures. So there is some kind of 3D information even within that. So there will be a possibility to interpret the data and mine that information out, the closest structure of these 10 nanometer size objects. Next slide, please. So obviously these come in all kinds of sizes and shapes. You can see a tiny one, 2.5 nanometer estimated size, sitting on the top, a little bit brighter. Why? Because there, since that little gold thing, extra gold is there, the emission is brighter there. You have a stronger signal. That's generally is not taken into account, but model-based measurements can do that. So that's why we believe that the modeling and simulation is so important. Next slide, please. So here is a little bit on the why modeling and simulation is important, both for TEM and SEM, is right where the border of a nanoparticle is, or any nano-object, which is, then it depends on the material, the landing energy, how many atoms you need in the path of the electron beam to be able to say that, okay, that's where the edge is, that's where the border of the particle is. Clearly not trivial. And what the ideal landing energy would be is that which one atom can stop, because that would give you a con. And that's not feasible really, but both for TEM and SEM, there is that border region, which can be easily a couple of nanometers for a 30 or 10 nanometer size particle, that is a significant region of ambiguity to deal with. And the best way to do that is through modeling and simulation, when you can interpret the results that if it looks like this, then it must be that. So then the next slide, please. Here is a comparison. I don't really want to go much into it. Shows that TEMs and SEM on the very same sample can get, so the same sample population can get very good quality results. Next one, please. So here is something that shows that depending on what size particles you measure, this was done by guys at PTB, what signal you can expect to get. And it's obviously the how many atoms are in the path of the electrons that is very important. They calculated this for sphere. And obviously these samples are not really spheres, but this is a step forward for sure. The lower image, which is moving, is a simulated SEM image of 10 nanometer wide, 30 nanometer tall structures. These are important for integrated circuit measurements. And these are very useful to check different software that can evaluate 2D and 3D properties. There's some surface roughness and height variation and so on. So this is a sample, and a series of SEM images played in a moving file have never ever seen an electron beam, only model. Slide, please, and simulation. So here are some examples, and on single computer, how long it takes to simulate a scene like this. This was a couple of years ago. Things improved somewhat, but it's still very, very important to speed up these calculations very well. So these are SEM images, again, generated by simulation and computer. Next slide, please. This one also is a very rough line generated with the computer. So this is how a super rough line will look like in the SEM tilted, because we wanted to evaluate the different software that claim that they can do 3D rendering of structures. And that alone is a completely different topic, how to do 3D measurements. But some level of viability there, the accuracy need to be improved, and the way to do it, again, through modeling and simulation. Next slide, please. Here is something where you can use the simulation and the modeling to predict likely results. So these are copper structures with a void in them. And we looked into it through modeling, that what chances are to detect them and what size you can still detect. And you can see down to some of the small sizes, we can see even 5 nanometer size voids inside a copper line. And whether backscattered or secondary signal is better to use for this, it depends. And again, what landing energy and other things. So this allows you to predict the results, calculate that what you are supposed to get. And that could be very powerful for be able to able to measure something. You can choose the imaging parameters better. Next slide, please. Yet another example for particles. So the structure is on the right. It's a cat structure with facets and stuff. In the case of gold, if you use 1 kilo electron volt landing energy, the transmitted electron signal will look like next to the CAD, the backscatter next to it, and the secondary next to it. If your task is to measure the particle size, then if you use the same thresholding algorithm on these 3 images, sizes will matter. If you go to the transition to the 0, then they will be the same. So you can use different algorithms from different signals to arrive a more accurate result and also speed up the measurement. The lower part shows that how the very same particle would look like under a 10 kilo electron volt, a 5 and a 200 eV and even a 50 eV electron beam if it's very sharp. So it shows that if your task is to resolve the surface structure and the small edges of that structure, the best is to go to low energy or even very low energy versus high energy when you are punching through a lot of atoms without generating much signal. So again, this is critical, and especially in the future when many of these measurements become at the true nanoscale important, that what to choose as your landing energy and measuring parameter, which signal, and so on. Next slide, please. So this is just about the conclusion. So electron microscopy is an indispensable part of scientific discovery and industrial production. The true nanometer, even sub-nanometer scale measurements of features and a possible atomic resolution with good accuracy is also feasible in some cases. So sophisticated imaging methods can further advance the performance of these microscopes. Physics-based models, simulations, another one. Further improvements in imaging resolution and so on are attainable, especially at low landing energies, and are all possible. So the point is, we need to still keep going. We need visionaries, excellent scientists and engineers like Professor Dasgupta show the way and lead us to the future of electron microscopy, which is indeed very bright. Thank you very much.
Thank you, Professor Andrus. Thank you showing wonders of ACM and electron microscopy and the factors that should be taken care of to get the good quality images and what are the future possibilities to further improvement. Thank you so much for your time. Again, if any questions will be there, then you will be contacted by email ID, your email.
Yeah, absolutely. Would be glad to. Yeah. Just don't hesitate.
For your time. Yeah, thank you, sir.
Yeah, thank you.
Yeah. So now to go ahead, I invite Dr. N. Satish, Joint Secretary EMSI and Principal Scientist CSIR-AMPRI for vote of thanks. Dr. Satish.
Thank you, Dr. Archana. So thank you all for this thing. It is my pleasure to give the vote of thanks for this wonderful workshop. So it has been very much enlightening for us to listen very good talk on 2D materials to the graphene and carbine to the like graphidine and all. So it was very interesting talk. So first of all, I would like to thank our distinguished speakers, Professor Polikal M. Ajayan and Professor Andrus Veladar and Professor Carlo S. Casari. So they have been very kind to us for delivering such a wonderful lecture, and the information they have provided in these lectures are enormous. So we would like to observe it, and we can watch it again, and it will be available in YouTube, so that we can like get to know the information and learn more about this frontiers in material science and also the standardization of this electron microscopy of this one. So then I would like to thank Professor Kamana Chattopadhyay for chairing this workshop and his guidance and his like wishes for the successful of this workshop. Then I would thank our director, Dr. Avanish Kumar Srivastava, for initiating the workshop and his vision to make this workshop successful. And he's also guiding us as a president of PMSA also to guide us into the successful workshop. I also thank Dr. Archana and Mr. Narendra for helping in this workshop. And like I thank Electron Microscope Society and also the Electron Microscope Society Executive Council. And I thank all of the CSIR-AMPRI fraternity for supporting this workshop, making it successful. And last but not least, I thank all the audiences and who has been joined in YouTube channels and also in our Zoom. And I thank all the audience at this our time and listening until without going for lunch, for dinner, and listening such a wonderful talks in the evening. And thank you all for the wonderful time and have a very nice evening. Thank you all.
Thank you, Dr. Satish. Am I audible?
Yes, yes.
Okay. Thank you so much. Before we end up, I invite EMSI President, Professor Avanish Kumar Srivastava, for his final comment. Sir, please.
So thank you very much and for having this kind of patience we had. Sorry. We had wonderful talks from 3 speakers, and I fully agree with Dr. Satish, the kind of session we had. It was so interesting and meaningful lectures that on views, I just I'm told that there were more than 2,300 views already who have participated in this lecture series today in 3 lectures. Last but not least, I thank the chairman of this workshop too, because he took a lot of interest to shaping this workshop. And if I am allowed, I would like to call Professor Shrikant Lele, the present in this among audience. I can see on Zoom his name is reflecting, so probably he is linked. And if he can say 1 or 2 minutes, the concluding remarks. Professor Lele, are you there? Professor Shrikant Lele? Professor Shrikant Lele. So I think he's not there, but I can see his name. So he joined and probably. Professor Lele, your mic is mute.
Yeah, can you hear me? I think I have unmuted now.
And now I can hear you, yes.
Yeah, I mean, I think I'll join Dr. Satish and you in thanking all the speakers. They're wonderful lectures. I'm not an electron microscopist myself, but they're extremely informative. And for those who are doing electron microscopy, I think
I'll call you later. Hey, Chandru, I'll call you later.
The limits of microscopy can be increased even without changing your microscope. Of course, I mean, the capabilities of the modern microscopes have improved enormously over time. But even with whatever one has, by just doing the right things as far as the microscope settings are concerned, one can get far better images. And by coupling modeling, you can improve it further. That is something which I knew, but I did not know the extent to which one can improve the images and therefore extract much more information than is normally available. So I would like to once again join everybody in thanking all those concerned who have given the lectures and those who have participated, and I'm sure that they will benefit from all the learning which has gone on in these lectures. And as was mentioned, they are available on YouTube, so one can look at it even later and keep on learning with time as one learns more and more. Thank you.
Thank you, sir. Thank you. So if there is no comment or Professor Chattopadhyay wants to have concluding line, you are muted, sir.
I just wanted to thank all of them, but particularly I want all the younger people who are listening to Andrea's lecture.
Yeah.
From the beginning of our microscope, we have learned to do something. There's a culture which I find that present generation students does not follow. For example, when you take a good picture of a good area, you don't hover around the area too long. You go to other areas and then decide what you want to measure, what you want to do, then quickly come to that area and take photograph. Second thing is that when you take photographs, you hold your breath, whether it is SCM or TM, you hold your breath, you stay completely silent and then take the picture. These are the practices nowadays are not done. And you see, ultimately what he talked about is actually a demonstration of and automations of those effects, so that you can do enough Fourier transform and see that those are there and you can filter it out. I know that not everybody will have access to those, but even those who have not access, they can have some practices which will eliminate quite a bit. Just like a chiller, people don't tune the chiller that temperature is constant or near constant. The fluctuations is less. I find that people think the chiller is a black box. You don't have to worry. And it can on and off at whatever temperature interval, it doesn't matter. Nobody, I find that most of the places tune the chiller to have a soft, their controller have a soft landing so that the temperature difference is very, very small. And he has shown that I was very fascinated by seeing that, although it is obvious that how much noise it can generate. So I really thank you for demonstrating all these things rigorously, and people should use those rigorous methods. But if you do not have the method, still they can get a better image by having a good practice. That is the only thing I want to tell.
Thank you very much for your kind words and the lesson and the message to youngsters who are beginning in this field, especially the ME students and PhD students, because they have to go a long way. And I said there, as I said, there are more than 2,000 views. People are watching and listening these lectures. So I'm sure these lectures will be very useful for them, for everybody, in fact, because a lot of thoughts in terms of material science applications and electron microscopy instrumentation and advancements as well. So with this, thank you very much to all of you for this wonderful evening in India and wonderful morning in the US and wonderful afternoon in the Europe. Thank you very much.
Thank you, sir. Thank you for that. Yeah, good.
Thank you.
Thank you. Thank you, Carlo. Thank you.
Bye-bye.